नमस्कार, आदाब, सत श्री अकाल, कैसा है, केम छो, हेलो एंड वेलकम इन गेट वाला. So student, this is one short series, and in one short series today I am going to start new subject machine design. Today we are going to start new subject machine design, and you already know in one short series, in one lecture we complete one topic of any subject. So the topic which we are going to complete in today's class is break. Means today we will complete the topic break. So we are starting. Before starting, it is brief introduction about me. As you all know, I am Ramanand Bansal. I have cracked GATE in 2014 with All India rank 70. After that, I got selected in IOCL, HPCL and BARC. Finally, I have joined IOCL as Operation Officer in Hazira Terminal, Surat. In IOCL, after working for 1 year, I left the job to pursue my passion towards teaching, and since then, I am teaching in the field of GATE and ESE. So, it is brief introduction about me. Now, without any delay, we are going to start our today's topic of this machine design subject, and that topic is break. Okay. So, it is the lecture flow of today's lecture. In break, first we will discuss introduction of break. In this, we will discuss what is break. After that, we will discuss various types of break. And in various type of break, in our syllabus, we have to study two types of break, shoe break and bend break. So after that, we first will start shoe break and we'll discuss the analysis of shoe break. After completing this analysis, we will understand what is self-energizing break and what is self-locking condition. After this, we will study various cases of shoe break. Then we will see maximum pressure on shoe break. Okay. After that, we will start another type of break, that is bend break. So first we will discuss what is bend break and introduction of bend break. In bend break, we will study two types of break, simple bend break and differential bend break. So first we'll do the analysis of simple bend break and then we'll do the analysis of differential bend break. So this is the lecture flow of today's lecture. So first I am starting our first topic, that is introduction of break. In introduction of break, we'll understand what is the definition of break. And I think you already know, all of you know what is the actual definition of break. What is break? Break is defined as a, one second. Break is defined as a device which is used to absorb the energy possessed by a moving system or mechanism. Means it absorbs the energy of a moving system by using friction. Means brake is the device, or you can say mechanical device, which absorb the energy of a moving system by means of friction. Now what is the objective to absorb this energy? You already know. To slow down or completely stop the motion of a moving system such as rotating drum, machine or vehicle. This is the application of brake. Means through brake what we do, if we want to reduce the speed of any moving system, or we want to completely stop the moving system by means of friction. So for that, the device which we use is known as brake. Means brake absorb the kinetic energy of a moving system by means of friction to reduce the speed of system or completely stop the moving system. Okay, so this is the definition of brake. In brake, we will study various types of brake. There are various types of brake: mechanical brake, hydraulic brakes, electrical brake. Now mechanical, our study is only limited to mechanical brake. Now in mechanical brake also further classified as radial brake and axle brake. Radial brake is further classified as external brake and internal brake. In external brake further classified as shoe brake and bend brake. Internal brake is internally expanding shoe brake. But in our syllabus, we have to only study external brake, that is shoe brake and bend brake. So in today's lecture, we will only study shoe brake and bend brake. And first we will start with shoe brake. So I am going to start shoe brake. This is the basic diagram of shoe brake. In this diagram, this link is drum. In this diagram, this link is drum. And this drum is rotating, like in this diagram it is rotating in clockwise direction. Our objective is to apply brake in this drum. Means we want to get braking action in this drum, and to get braking action in this drum, the device which I am using, or the brake which I am using, is this, and this brake is nothing but shoe brake. It is the diagram of shoe brake. Now in this shoe brake, this green portion and this white portion, this portion completely known as lever of the brake. So it is known as lever of the brake. Lever of brake. Okay. So this portion is lever of brake. Now you can see this lever is hinged at this location. Yes sir, this lever is hinged at this location. I am denoting this location as point O, and this point O is known as fulcrum. Means what is the definition of fulcrum? The point at which brake lever is hinged. The point at which brake lever is hinged, that point is known as fulcrum. So here point O is known as fulcrum. Now this white portion of this lever, this white portion, this white portion of this lever is known as shoe or block. So this white portion of this lever, is known as shoe or block, and this shoe or block makes directly contact with this drum. And to apply the brake in this drum, we are using friction. So what we will do, in below side of this shoe or drum, we will attach a friction lining. Friction lining is nothing but it is the material of high coefficient of friction. So in below side of this shoe or block, we will always attach friction lining to ensure high coefficient of friction between the shoe and drum. So this is nothing but friction lining. Okay, so this is the basic naming of shoe brake or basic diagram of shoe brake. Now our objective is to apply braking action or apply brake in this drum. To apply brake in this drum, we will apply a force in this lever. The force which we are applying in the lever to get braking action in the drum is known as braking effort or actuating force. Again I am repeating, what is braking effort or actuating force? The force which we are applying in the lever to get braking action in the drum is known as braking effort or actuating force. Suppose I am denoting braking effort or actuating force is capital P. So what is capital P? It is the force or effort which we are applying on lever to get braking action in drum. Okay, so the force which we are applying in lever to get braking action in drum is known as braking effort. Now what we want, this is our input force, this is our input because effort is input, and you already studied mechanical advantage. Mechanical advantage means to get any output, the input we want, input should be as much as low possible, means effort should be as much as low possible. That is known as mechanical advantage. So what we want braking action or braking effort in this drum, and to get the braking action or braking action or braking effort, braking action in this drum, the effort which we are applying in the lever is braking effort, and that effort we want as much as low as possible. For that we will apply braking effort in this drum in this location. A little later I will explain why I am applying braking effort in this at this location. Suppose at the location where we are applying braking effort, I am denoting this location as point A or point O. Sorry, point O nahi. O is this point Q. Now at this location we want to apply braking effort. Now what should be the direction of braking effort? The direction of braking effort or this location should be vertically downward. Why? I am denoting braking effort as P. Now but why I am applying braking effort in downward direction, vertically downward? Why? Ultimately our objective is to apply braking action in this drum. To get braking action in this drum, we need to connect this shoe or friction lining with the drum in pressurized condition. To get pressure between this shoe and this drum, this shoe should try to come in downward direction, because whenever this shoe will try to come in downward direction, it will try to push in drum in downward direction. But since drum is hinged at this location, drum will not move in downward direction, and pressure will create between shoe and drum. So to create pressure between shoe and drum, this shoe should try to move in downward direction, and to move shoe in downward direction, there should be if this shoe is want to move in this downward direction, there should be movement of, there should be a force, we need to apply our effort in this lever such that it should create a movement about this fulcrum O in clockwise direction. Because if you will focus in this direction, due to this direction movement about O is clockwise, means what we will want, the motion in shoe should be such that it should try to push the drum in downward direction. For that we need to try to rotate this lever about O in clockwise direction, and to rotate this lever about O in clockwise direction we need to apply a braking effort P at this location in downward direction, because the movement of this downward force about O is clockwise direction, and this movement will try to push this shoe in downward direction, and it will create pressure between the shoe and drum. Due to that pressure force, normal force will come, due to normal force friction force will come, and due to friction force braking action will induce in the drum. Okay, so the direction of braking effort should be vertically downward. Now I have told you that we need to apply this braking effort at this location Q. If we want, we can also apply, if you want you can also apply braking effort at this location also. Okay, but suppose the braking effort which I am applying here is P1, and if I am braking effort I am applying here, that braking effort is P. Now you can see the distance of this location from fulcrum O is maximum, and distance of this location from fulcrum O is less than this distance. Suppose this distance is L, just for understanding, and this distance is L1. So you can see L is more than L1. L is maximum actually. Now what will happen, due to this force, since distance is maximum, the moment about O will be maximum as compared to moment about this force, if force is same. Means can I say by using the same effort, if I am applying effort from the farthest point from point O, the effect of that effort about O in terms of moment will be maximum. Due to this, pressure created between this shoe and drum will be maximum. Due to that, normal force will be maximum, and if normal force is maximum, friction force will be maximum, and if friction is maximum, the friction torque, that is braking torque, will be maximum. Means if I am applying braking effort here, with same braking effort I will get more braking action in this drum. Means this point applying braking effort at this point is more better than applying braking effort at this location, because by applying same braking effort at this location we will get more braking action in this drum. Braking action means braking action which we are getting in drum to reduce or the motion of drum, or to completely stop the motion of drum. Okay, so now you need to remember this, the braking effort at the location at which we will apply braking effort will be farthest from this fulcrum O, which is in this case is point Q. That's why we are applying braking effort at this point Q. Now direction of braking effort should be such that it should try to move this shoe in this direction, which will create pressure between shoe and drum. For that we need to apply braking effort at this location in downward direction. Okay, and this P is known as braking effort. So this is brief introduction about shoe brake. Now we need to discuss the detailed analysis of shoe brake. But before doing the detailed analysis of shoe brake, first we need to understand what is short shoe brake, what is short shoe brake and what is long shoe brake. Now one more terminology you need to understand. In shoe brake, this angle, I am denoting this angle as 2 theta. Okay, this portion of the drum is making contact with shoe or friction lining, and this portion is making angle 2 theta. This 2 theta angle is known as angle of contact or block angle. Angle of contact or block angle. Some author refer this angle as theta. As per my notation, block angle or angle of contact is 2 theta. If examiner has given block angle, means 2 theta is given. If examiner has given semi block angle, means theta is given. Okay, because as per my notation, block angle is 2 theta. Now we will discuss what is short shoe brake and what is long shoe brake. If angle of contact, you can easily understand. If angle of contact 2 theta is less, then this portion width of this portion will be less. In that case, that brake will be known as short shoe brake. If angle of contact, that is 2 theta, angle of contact, that is 2 theta, is more, means this portion will be more, then that brake is known as long shoe brake. Okay. For that, you need to remember a value pi by 4. Now you can easily relate. If angle of contact, that is 2 theta, is less than pi by 4, is less than pi by 4. Okay. Here I am denoting angle in radian. If angle of contact or block angle is less than or equal to pi by 4, then that brake will be known as short shoe brake. If angle of contact or block angle, that is 2 theta, is more than pi by 4, then that brake is known as long shoe brake. Okay. So I am also simplifying here. If 2 theta is less than pi by 4 or equal to pi by 4, then that brake will be known as short shoe brake. If angle of theta or block angle, that is 2 theta, is greater than pi by 4, then that brake is known as long shoe brake. Okay. Okay. This distribution we will use whenever in exam type of brake is not mentioned, whether it is short shoe brake or long shoe brake. If examiner has mentioned the brake is short shoe, then we need not to see 2 theta. Whatever the value of 2 theta, we will consider that brake as short shoe brake. If examiner has mentioned that brake is long shoe brake, then whatever the value of 2 theta, we will consider that brake as long shoe brake. Okay. Now, in short shoe and long shoe brake, if here you will draw the pressure distribution, this portion of this drum is making contact with shoe. Here, this portion of this drum is making contact with shoe. This is short shoe brake and it is long shoe brake. Okay. In short shoe brake, this region will be very less because 2 theta is less. In long shoe brake, this region will be large. Now suppose I am denoting this region as B, A, C, whose center point is A. Again, I am denoting this region as B, A, C, whose midpoint or center point is A. Okay, midpoint or center point is A. Now, due to braking effort, pressure will induce between shoe and drum, and the pressure distribution between this shoe and drum will be roughly like this. I am drawing pressure distribution. You need not to remember the exact pressure distribution, only you need to remember that pressure at midpoint, that is A, will be maximum, and when you will move in this side means when you will move far from point A, the pressure will reduce. Same distribution will be here. Pressure will be maximum at point A, and when we will move in this side, pressure will gradually reduce. But we need not to remember the equation of this. Now, what I am trying to say, okay, what I am trying to explain here. If 2 theta is less, if 2 theta is, that is angle of contact is very less, means brake is short shoe brake. In that case, we can assume this surface BAC as flat surface. BAC as flat surface. We can assume, actually it is not flat, but for short shoe brake, because 2 theta is very less, so it will be nearly flat because 2 theta is very less. So we can assume this BAC surface as flat surface, and we can assume this pressure distribution is uniform. Pressure distribution is uniform. This thing I am discussing for short shoe brake. Pressure distribution is uniform. Means in short shoe brake, we can consider the region which are making, or region of drum which is making contact with shoe, we can consider that region as flat surface, and we can assume that pressure distribution in that region is uniform. Actually it is not uniform, actually it is not flat, but for short shoe brake we can assume or consider this portion as flat, and we can assume pressure distribution is uniform. Means for short shoe brake, if I will draw this BAC portion separately, we can imagine or refer this as flat surface, and we can assume or pressure distribution is uniform. But this thing is only valid for short shoe brake, but we cannot make this assumption for long shoe brake because this angle is more and this angle is more, therefore we cannot assume this surface as flat surface for long shoe brake. Now, how we will do the analysis of short shoe break and long shoe break? Here you can understand one important point. In short shoe break, we can consider this region BAC as flat surface and pressure distribution is uniform. Now what we will do? Now what we will do in short shoe break, or whether you are talking about short shoe break or long shoe break, the midpoint of this contact region is point A. So what we will do, we will replace this entire pressure distribution with equivalent normal force, which we will refer as capital N. And capital N will always act in point A, whether it is short shoe break or long shoe break. Means what we can assume, entire the normal force due to this pressure distribution, which I am denoting as capital N. What is capital N? Capital N is total normal force on the friction lining or total normal force on the drum due to pressure. Okay, and that total normal force or resultant normal force will always act at point A, because this pressure distribution is symmetric. Okay, so total normal force will always act at point A, whether it is short shoe break or whether it is long shoe break. And point A, what is point A? Point A is the midpoint of contact region BAC. So normal force will always act at point A. Okay, now direction of this normal force will always be from in the FBD of drum. Here we are drawing the FBD of drum. Direction of this normal force will always be from point A towards the center of the drum. The direction of this normal force will always be from point A towards the center of this drum. This thing I will also explain later. But this is in whether it is short shoe break or long shoe break, we can replace entire pressure distribution with equivalent normal force, which is capital N, which will always act at point A. Direction of this normal force in the FBD of drum will be from point A towards center, from point A towards center. So it is normal force. Now due to this normal force, friction force will come. Now in mechanics you already studied, if normal force is N, friction force will be perpendicular to N and its magnitude will be mu into N, where mu is coefficient of friction. But it is not always correct. This concept is only correct when the surface is flat surface and pressure distribution is uniform. In the concept of friction, I think you studied, if this surface is making contact with any surface, suppose this is fixed, the velocity of direction of this block is this. In this block, suppose if we will draw drawing FBD, normal force N is coming in this side. This is flat surface and here pressure distribution is uniform. So pressure distribution is uniform and it is flat surface. Then if normal force is N, friction force will be mu into N, where mu is coefficient of friction between this block and the surface, and it will be opposite to the direction of relative motion. Right now relative motion in this block is occurring in this direction, so friction force will be in this direction. But this is valid for flat surface when pressure distribution is uniform. Now what I told, for short shoe break we can consider this surface as flat surface and pressure distribution is uniform. Means can I use this concept for short shoe break? Yes sir, this concept you can use for short shoe break. Means in this break, this is the diagram of short shoe break and here normal force is N. So here can I say friction force will be mu into N, it will be perpendicular to N. Right now N is vertical, so mu N will be horizontal and friction force will be mu into N. Because in short shoe break we are referring this surface as flat surface and we are assuming pressure distribution is uniform. So this concept is valid for short shoe break. Now you can say what will be the sense of friction force, whether it will be this side or this side. Right now I am taking the sense of friction force this side, but how you have taken? Right now I am not mentioning what is the direction of this drum. If this drum is rotating clockwise, friction force will be this direction. Suppose I am assuming drum is rotating clockwise. If this drum is rotating anti-clockwise, then friction will be in this direction. But right now I am not explaining how you need to find the sense of friction force, that I will explain later. Here I am only explaining if normal force is N in short shoe break. In short shoe break we can apply this concept directly, because in short shoe break we are assuming referring surface as flat surface and we are assuming pressure distribution is uniform. So if normal force is N, we can say that in short shoe break friction force will be mu into N. It will be perpendicular to N and opposite to direction of relative motion. But right now drum is rotating clockwise, so its direction will be this, its sense will be this. But I am not here I am not explaining How to find sense of this friction force, that I will explain later. Here I am explaining for short shoe brake, if normal force is n, friction force will be mu into n. It will be perpendicular to n. This is important. But for long shoe brake, how we can find the friction force? Because for long shoe brake this concept is not valid. Why? Means friction force will not be equal to mu into L. It is 100% sure. Why? Because for long shoe brake we cannot assume pressure is uniform, and for long shoe brake we can also not assume this surface as flat surface. So for long shoe brake, while calculating friction force, instead of using n, friction force will be perpendicular to n. It is 100% sure. If it is short shoe brake, friction force will be mu into L. But for long shoe brake, instead of using actual coefficient of friction, that is mu, we will replace that coefficient of friction with equivalent coefficient of friction, that is mu e. And I will write the formula of equivalent coefficient of friction for long shoe brake. And friction force will be mu equivalent into n. Means what is the difference in this diagram? In this diagram means for short shoe brake and for long shoe brake. In both diagram, n is normal force. Now in both diagram, friction force will be perpendicular to n. Now for short shoe brake, magnitude of friction force will be mu into n, where mu is actual coefficient of friction. But for long shoe brake, the magnitude of friction force will be mu equivalent into n, where mu equivalent is equivalent coefficient of friction. Mu equivalent is equivalent coefficient of friction or mean coefficient of friction. Now how to find mu equivalent coefficient of friction or mean coefficient of friction for long shoe brake? I will write the formula for that. But this is the concept. Means if I will summarize whole this discussion, can I say whether it is long shoe brake or short shoe brake, at this point A, we will apply at this point A. Point A is the midpoint of this contact region. Okay. And while doing the analysis, entire contact region, we can replace that contact region with single contact point, that is A. And in this single contact point A, total normal force N will act, whose direction will be from point A towards center of drum. Now perpendicular to N, friction force will act. Okay, if drum is rotating clockwise, then direction of friction force will be this. But right now I am not explaining the direction of sense of friction force. It will be perpendicular to N. But how to find sense, that I will explain later. But here I am explaining how to find the magnitude of friction force. So you can say the magnitude of friction force will be mu equivalent into N. Always use mu equivalent into N. And for short shoe brake, can I say mu equivalent will be equal to mu? For short shoe, means mu equivalent will be mu, that is actual coefficient of friction. And for long shoe brake, we need to calculate mu equivalent. And for long shoe brake, the formula to calculate mu equivalent is 4 mu sine theta plus 2 theta plus sine 2 theta. In above side sine theta is coming, here sine 2 theta is coming, where 2 theta is block angle. Where 2 theta is block angle. And here put block angle in radian. Radian, not in degree. Why, sir? Whenever angle is coming inside sine or cos, whether you are putting angle in degree or radian, it will not matter. Okay. But if angle is coming outside, it must be in radian. So here put 2 theta in radian. This formula is for long shoe brake. Means now analysis will become very simple. Whether it is short shoe brake or long shoe brake, replace this whole contact region with single contact point A, which is midpoint of contact region. In that single contact point, normal force will act, and it will act, which direction will be from in that F body of drum, from point A towards center of drum. Now perpendicular to N, friction force will act come. Now whether it is short shoe brake or long shoe brake, the formula to calculate friction force will always be mu equivalent into N, where N is normal force and mu equivalent is equivalent coefficient of friction. For short shoe brake, mu equivalent will be equal to mu, and for long shoe brake, the formula to calculate mu equivalent is this. And if 2 theta is less than pi by 4 or equal to pi by 4, that brake will be short shoe brake. If 2 theta is greater than pi by 4, then that brake will be long shoe brake, and apply this formula to calculate mu equivalent. And if examiner has not mentioned whether brake is short shoe or long shoe, and examiner has also not given the value of block angle, that is 2 theta, then always consider that brake as short shoe brake. Means directly use mu equivalent is equal to mu. So this is the difference between short shoe and long shoe brake. Okay. Now if you understood this concept, you will easily understand how to do the analysis of shoe brake. So now I am doing the analysis of shoe brake. For that I am considering this brake. Suppose in this brake P is braking effort. Suppose this distance is A. this mid contact point I am referring as A. When I will draw the FBD of drum and shoe, we will replace this whole contact region with single contact point A. Okay. Now the vertical distance of this point A from fulcrum, always see the vertical distance and horizontal distance of this point A from fulcrum. Vertical distance of this point A from fulcrum is A. The horizontal distance of this point A from fulcrum is suppose B. Now suppose this distance is C. Now I am doing the analysis of this shoe brake first for clockwise rotation of drum. So right now I am doing this analysis for clockwise rotation of drum. So drum is rotating clockwise. Here braking effort P is acting. This distance is A, this distance is B, this distance is C. Now for the analysis what we will do, we will always draw the FBD of drum and lever. FBD of drum and lever. And in drum and lever, contact point is point A because we are replacing this entire contact region with single contact point A. So what we need to do, when we will draw the FBD of this drum and lever, we need to find the contact force at this location A in the FBD of drum and in the FBD of lever. And you already in engineering mechanics subject you have studied how to draw FBD. If we are able to find the contact force which are acting at contact point A in the FBD of drum, then equal and opposite contact force will act at point A in the FBD of lever. Okay, if any force at point A in the FBD of drum is acting like this, equal and opposite force at point A will act in the FBD of lever at point A. Now what we will do, always first we will find the direction of contact force at location A in the FBD of drum. Means always we will first draw the FBD of drum because it will be easier for us to draw the FBD of drum than the FBD of lever. Okay, how we will draw? At location A, first we will find the normal force N in the FBD of drum. I am denoting normal force as capital N. Now the direction of normal force in the FBD of drum will always be from point A towards the center of drum. It will always be like this. Means direction of normal force, that is N, in FBD of drum will be from point A towards center of drum. Means like it will be like this. It is very simple. It is the direction of normal force N. Now what about friction force? Friction force will always be perpendicular to N. Right now N is vertical, so it will be horizontal. Now sense. So in the FBD of drum, listen carefully, in the FBD of drum, but you need to draw friction force in FBD of drum. In the FBD of drum, direction of friction force at point A will be opposite to direction of velocity of A, because in drum friction is trying to reduce the speed of drum, and if it is trying to reduce the speed of drum, definitely it will act opposite to the direction of velocity of point A. So right now drum is rotating clockwise, so direction of velocity of point A will be this, and in FBD of drum friction will act opposite to the direction of velocity of A. Since velocity of A is acting in this direction, friction force in the FBD of drum will be in this direction. Now magnitude of this friction force will always be mu equivalent into N, where for short shoe brake mu is equal to mu. For long shoe brake, formula to calculate mu equivalent I have already explained. Okay, so it is the FBD of drum. Now the contact force in the at point A in the FBD of lever will be equal and opposite to the contact forces which are coming in the FBD of drum. In FBD of drum at point A, contact force N is coming downward, so in FBD of lever contact force N will be upward. Very simple. In FBD of drum, contact force at point A is acting in this direction, mu equivalent into N, so here friction force will be in this direction. Okay, so this is the FBD of lever and FBD of drum. It is very easy to draw. Now if in the from the FBD of drum, if we will calculate braking torque, what will be the formula to calculate braking torque? It will be, braking torque is coming due to friction. You can also, how to calculate braking torque? Force into perpendicular distance. Here you can see the distance of perpendicular distance of this N from this hinge point is 0, because it is the line of action of N passing through this point O. So braking torque will only come due to this friction force, and it will be mu equivalent into N, that is friction force, into perpendicular distance of this friction force from this point, which is equal to the radius of drum. Suppose I am denoting radius of drum as R or small r, so it will be small r. You can remember this formula, because in shoe brake, formula to calculate braking torque will always be this, that is mu equivalent into N, that is friction force, into radius of drum. Okay, now Another important point is we need to find the relation between P n and mu equivalent into n, that is friction force. How to find the relation? For that, always in the always take net moment about this fulcrum O about 0 in the body of lever. Means to find the relation between P n and friction force in the body of lever, not in drum, in the body of lever. It must be in the body of lever. Always take summation of moment about fulcrum O 0. Why I am taking? You can take moment about any point in this lever, but why I am taking for moment about fulcrum O? Because if we'll take, because in this fulcrum O, this lever is hinged. So here this hinge reaction will also come. Suppose it is acting like this. But if we are taking moment about fulcrum O, the moment of reaction of this location about O will be 0. Means while we are taking moment about fulcrum O, we need not to bother about the reaction which are coming at this location, because moment of the reaction which are coming at location O, about moment about O for those forces or those reaction will be 0. Means while taking the moment about fulcrum O, we need not to bother about reaction which are coming at this location, and our calculation work will become easier. So we will always take net moment about fulcrum O. Now how will take? While taking this equation, suppose I am considering clockwise movement as plus or anti-clockwise as minus. If you want to take anti-clockwise as plus, clockwise as minus, you can take, but follow any one convention. I am taking clockwise as plus. So what will be the moment of this effort P about O? It will be P, and perpendicular distance of P from O is B plus C. So moment will be P into B plus C. Now direction of movement of due to this effort P about O is clockwise, and I am considering clockwise as moment as positive. Now moment due to this force N, it is N. Now perpendicular distance of this N from O is B. So moment will be N into B, and direction of movement will be anti-clockwise. I am considering clockwise as plus and anti-clockwise as minus. Now friction force. Friction force is mu equivalent into N. Due to this is force. Now its perpendicular distance from point O. Since friction force is horizontal, we need to see vertical distance. Vertical distance is A. So direction of movement of this friction force is mu equivalent into N into A, and direction is clockwise. I am considering clockwise as plus. Now this is equal to 0. Why I have not considered this reaction? I consider these reactions, but moment of this reaction about O will be 0. So we need not to write this. Now after simplifying this, if you will calculate the expression of P, it will come NB minus mu equivalent NA divided by B plus C. Okay. This is one important relation. Now if examiner is asking what will be braking effort, so definitely he will give braking torque. So from this relation we can find N. After calculating N, from this relation we can calculate braking effort. Similarly, if examiner has given braking effort, he will ask about braking torque. So if braking effort is given, from this relation we can calculate N, and by putting the value of N here we can calculate braking torque. Okay, but in exam you have to, if you want, you can remember this formula, because formula of braking torque will always come mu E into N into R, but you need not to remember this formula, because based on diagram this formula will change. How to find this relation? For that, always draw the body of drum and lever. First draw the body of drum, after that draw the body of lever. After that, in the body of lever, take net moment about fulcrum of 0. You will automatically get this relation. You need not to remember this relation. Okay, if you want, you can remember this relation, but you need not to remember this relation, because from case to case the expression of P can change based on these equations or this moment equation. Okay, but you need to remember this step, understand this step. Means first draw the body of drum. How to draw a body of drum I have already explained. Then draw the body of lever. In body of lever, always take net moment about fulcrum O equal to 0. Okay, to again explain this, I am taking one more case. In this case diagram is same, but I am considering drum is rotating anti-clockwise instead of clockwise. Okay, this is fulcrum O, this distance is A, this distance is B, this distance is C. I am replacing this whole contact region with single contact point A. Now again drum is rotating anti-clockwise. This point, single contact point is A, which is midpoint of this contact region. This is fulcrum, this distance is A, this is B, this is C. Radius of drum is R, but drum is rotating anti-clockwise. So what we will do? Again, first we will draw the body of drum. How to draw? First we will draw body of drum at contact force A. First we will draw normal force N. and normal force N will always act from point A towards center. For that it should act in vertically downward direction in abody of drum. Now friction force. Friction force will always be perpendicular to N. Okay. But in this direction, sense of friction force will be such that it should be opposite to the direction of velocity of point A if you are drawing friction force in abody of drum. So right now I am drawing friction force in abody of drum. So first find the direction of velocity of point A. Since drum is rotating anti-clockwise, direction of velocity of point A will be this, and friction force will act opposite to this, means friction force will be in this direction. And since and what is the magnitude of friction force? It will always be mu equivalent into N. For short shoe brake, mu equivalent is equal to mu. For long shoe brake, how to calculate mu equivalent, that I have already explained. Now the equal and opposite contact force at location A will come in the abody of drum. So in in abody of lever. In abody of drum, N is coming vertically downward. So in abody of lever at point A, N will be vertically upward. In abody of drum, friction force is coming in this direction. So in abody of lever at location A, friction force will act in this direction. Okay. And after drawing this abody of lever, in abody of lever, we will always take net moment about fulcrum O equal to 0. Okay. And suppose I am considering here effort P is coming in this direction. Suppose I am considering clockwise direction as plus and anti-clockwise movement as minus. So what will be the moment of this effort P? This effort is P. Its perpendicular distance from O is B plus C. So it will be P into B plus C. Now direction of movement due to this effort P about O is clockwise. So suppose I am considering clockwise direction as positive. Now moment of this N, this is N. Its perpendicular distance from O is B. So moment due to this N about O will be N into B. And direction of movement due to this force N about O is anti-clockwise. I am considering clockwise as plus, so anti-clockwise as minus. Now direction movement due to this friction force is mu equivalent into N. Now moment due to this will be friction force is mu N. Its perpendicular distance from point A is A, because since friction force is horizontal, we need to see vertical distance from point O, which is A in this case. Now direction of movement of friction force about O is anti-clockwise, and I am considering anti-clockwise direction as minus. Okay. Now moment of reactions of this hinge point, moment of reaction at this location or at this hinge about hinge point will be 0. So we are not considering this reaction. So it will be net moment about fulcrum which will be 0. From this, if we will find the relation of P, it will come NB plus mu equivalent Na divided by B plus C. You can see this relation is different, this relation is different. That's why I am saying don't remember or mug up this formula. Only understand the concept how we have find this relation. So it is the relation between effort P N and mu N. Okay. But if you will calculate the formula of braking torque, it will come again same. It will be mu N, mu equivalent into N into radius of drum. Why? Friction force is again mu equivalent in N to N. Whatever the direction of friction force, but it is again mu equivalent into N. Its perpendicular distance from this is R. So braking torque will be N. What is the direction of braking torque? Braking torque is coming in this direction is anti-clockwise. You can see the direction of movement due to this friction about this point is clockwise. And you can easily relate. Since drum is rotating anti-clockwise, objective is this braking torque is to apply braking action or to get braking action in drum. So definitely this braking torque will be opposite to the rotation of drum. Drum is rotating anti-clockwise. So definitely it will come clockwise. Like in this first case, drum was rotating clockwise. So definitely it will be anti-clockwise. You can check. It is coming anti-clockwise. Okay. And what we want by using the minimum FP, means by ensuring less effort, we want this braking torque should be more, because here braking effort P is our input, because we are applying that effort in the lever to get braking action in drum, and here braking action is this TB, means it is output. And what we want, with less input we want high output. Okay, so we want P should be P as much as low as possible, and we want TB as high as possible. Okay, so this is the analysis of shoe brake, and by using this concept we'll discuss some problems or questions first. Okay, so this is one first question. What this question is saying, Consider short shoe brake as shown in figure. This diagram is given. What you can see, suppose I am denoting this single contact point as A. The vertical distance of this contact point from fulcrum is 50 mm. Horizontal distance of point A from fulcrum is 100 mm, and this distance is 200 mm. Diameter of drum is given 300 mm. So radius of drum will be half of diameter, that is 150 mm. Suppose I am denoting radius as R. So in meter it will be 0.15 meter. Coefficient of friction is mu 0.3. Braking torque is given TB 300 Newton meter. Braking torque is given and it is 300 Newton meter. Now examiner asking what will be the braking effort for clockwise rotation of drum, means drum is rotating clockwise and we have to find braking effort, that is P. Now here first we need to find mu equivalent. Here examiner has already mentioned it is short shoe brake, and for short shoe brake mu is equivalent will be equal to actual mu, that is 0.3. Now what we will do, we will draw the FBD of drum and lever. Here braking torque is already given. Now what is the formula to braking torque? Mu equivalent into n into small r, where r is radius of drum. I have already told you for shoe brake, you can, if you want, you can remember this formula directly. Since braking torque is given, mu equivalent is given, radius of drum is given, we can find the value of n. Okay, so first we are finding the n. After finding the value of n, if you will draw the FBD of drum and lever, and in FBD of lever, if you will take the net moment about fulcrum O0, you will get the relation between P, n and mu equivalent into n. From that relation, since we have calculated the value of n, from that relation we can calculate the value of P. Very simple. So first I am calculating the value of n. Braking torque 300 Newton meter. Since I am taking braking torque in SI unit Newton meter, here we will put the value of radius r in meter. So we will get n value of n in Newton. Mu equivalent is 0.3 and we want to calculate r is radius of drum, which is 0.15 meter. From this relation, if we will calculate the value of n, we will get 300 divided by 0.3 divided by 0.15. So we are getting value of n is equal to 6666.667 Newton. Okay. Now we will draw the FBD of drum and lever. Okay, and in which direction drum is rotating? Drum is rotating in clockwise direction. Okay, this is contact point A. This is contact point A in the FBD of drum. This is contact point A in the FBD of drum. This is contact point A in the FBD of lever. Always first we will draw the FBD of drum, and in FBD of drum first we will draw the normal force A capital N. What will be the direction of normal force in the FBD of drum? It will be from point A towards center. For that we need to draw direction like this. So it is the direction of N. Now friction force. Friction force in the FBD of drum will always be perpendicular to N, means in this direction. Now in this direction, sense of friction force will be opposite to the direction of velocity of A if we are drawing the friction force in the FBD of drum. So first find the direction of velocity of A in FBD of drum. Since drum is rotating clockwise, so direction of velocity of point A will be this side. So definitely friction force, it is the direction of velocity of point A. So definitely friction force in the FBD of drum will be opposite to direction of velocity of A, when it will be in this direction. So this is the direction of friction force. I am denoting friction force as mu equivalent into N. Now we will draw this contact force N and friction force in FBD of lever. And in FBD of lever, the contact force at point A will be opposite to the contact force which are coming at the FBD of drum. Means in FBD of lever at point A, normal force N will be, here N is coming downward, so here N will come upward. Friction force will be, in FBD of drum, friction force is coming here, so in FBD of lever it will come here. It is the direction of braking effort which is already given in the question. Now in FBD of lever, we will take net moment about fulcrum O equal to 0. And while taking this moment, I am considering clockwise movement as plus and anti-clockwise movement as minus. So what will be the moment of this effort P? It will be effort P. Its perpendicular distance from fulcrum O. Since it is vertical, we will take horizontal distance, which is 100 plus 200, that is 300 mm. Now direction of movement due to effort P about O is clockwise. I am considering clockwise movement as positive. Now moment of due to this force N, It is n. Its perpendicular distance from O is 100. So moment will be n into 100. Direction of movement is anti-clockwise. I am considering clockwise as plus, so anti-clockwise as minus. 9. Direction of movement due to this friction force. This friction force is mu equivalent into n. And movement due to this friction force will be its perpendicular distance from O is 50. So it will be into 50. Now direction of movement this due to this friction force about O is clockwise. And I am considering clockwise direction as plus. And net movement around fulcrum O should be 0. From this relation we will get the relation of P. It will come, minus will come this side, so it will become plus n into 100. Plus will come here, this side it will become minus, it will become mu equivalent into n into 500 divided by 300. And we have already calculated is this. So effort P will be n is 6666.667 into 100 minus mu equivalent is 0.3 into n is 6666.667 into 500 divided by, sorry, it's not 500, it's 50. By mistake I have written 500, it is 50. So into 50 divided by 300. So from this equation we will get the value of P, that is braking effort. And how much it is coming? It is coming 1,888.889 Newton. So it is the value of braking effort to get this much of braking torque. Okay. So examiner has asked in braking effort in Newton, and we have already calculated braking effort in Newton, which is 1,888.889 Newton. Okay. Based on this concept, we will discuss one more question. It is another question. What this question is saying, the schematic diagram of an external drum rotating clockwise. This drum is rotating clockwise. This is important. Engaging with short shoe brake. Brake is short shoe. Short shoe means mu equivalent will be equal to actual coefficient of friction is shown in figure. The shoe is mounted at location Y on a rigid location. At this location shoe is mounted, which distance from hinge is already given. This distance are already given. A force F equal to 100 Newton, value of F is given, it is 100 Newton, is applied at the free end of the lever as shown in figure. The coefficient of friction between the shoe and drum is 0.3, means mu is 0.3, and since it is short shoe brake, mu equivalent will be equal to mu, means mu equivalent will always also be 0.3. Now examiner asking what will be the braking effort in Newton meter. So again, to find the braking effort, first we need to find formula of braking effort is mu equivalent into n into radius of drum. So first we need to find the value of n, and to find the value of n we need to find the relation between P, n and friction force. Okay, and from that relation we can calculate value of n because braking effort is given. Okay, okay. For that first we need to draw the FBD of drum and FBD of lever. So first I am drawing the FBD of drum and lever. This drum is rotating clockwise. From this diagram here already mentioned all dimensions are in mm, and in this diagram radius of drum is given, it is 100 mm. So radius of drum is 100 mm, in meter it will be 0.1 meter. Now suppose I am denoting this contact point which is midpoint of this region as A. So this contact point is A in the FBD of drum, it is the contact point A in the FBD of lever. So in first we will draw the FBD of drum, and in FBD of drum at contact point A we will find normal force. Suppose normal force is capital N. Direction of normal force in FBD of drum will always be from point A towards center, means in FBD of drum it will be like this. So it is the direction of normal force N. Now friction force is mu equivalent into N. It will be perpendicular to N. N is vertical, so it will be horizontal. Now in this direction sense of friction force will be such that it should be opposite to the direction of velocity of A when we are drawing friction force in FBD of drum. So first I am finding the direction of velocity of point A. Since drum is rotating clockwise, so direction of velocity of point A will be this, and in FBD of drum friction force will act opposite to this, means since direction of velocity of point A is this, friction force will be in this direction, and its magnitude is mu equivalent into N. Now in FBD of lever, the contact force which are acting at point A will be opposite to contact force which is acting in the FBD of drum, means in FBD of lever, contact force, normal force at A will be opposite to normal force which is coming in FBD of drum. In ability of drum, contact force N is coming downward. So in ability of lever, it will act in upward direction. In ability of drum, friction force is coming in this direction. So in ability of lever, at location F, friction force will come in this direction. Okay. Now after drawing this ability, in ability of lever, we will take net moment about fulcrum O. In ability of lever, will take net moment about fulcrum O equal to 0. And while taking this moment, I am considering clockwise direction as positive and anti-clockwise direction as negative. So the first moment due to this effort F, this force is F, its perpendicular distance from O is 300 mm. So moment will be F into 300. Direction of moment due to this force F about O will be anti-clockwise. Suppose I am considering anti-clockwise as minus and clockwise as plus. Now the moment due to this N, this force is N, its perpendicular distance from O is 200, you can see. Now direction of moment due to this force N about O is clockwise. I am considering clockwise as plus, so it is plus. Now this friction force, which is mu equivalent into N. Now moment due to this friction force, its perpendicular distance, since it is horizontal, we need to see vertical distance. So its vertical distance from point O is 300 mm. Its magnitude. Now direction. Direction of movement due to this friction force about O is anti-clockwise, and I am considering anti-clockwise direction as negative. And since we are taking movement about O, so moment of reaction which will come at location O about O will be 0. So we need not to bother about those reactions. So it is the summation of moment about fulcrum O which will be equal to 0. Now in question, value of F is already given. It is 100 Newton. So F is 100 into 300 plus N into 200. Mu equivalent is also given. I think mu equivalent is equal to mu, which is 0.3. So minus 0.3 into N into 300. So you can see in this relation only unknown N is coming, and from this relation if you will find the value of N, it will come, this minus will come this side, it will become 100 into 300. Now from this we can take N common, so it will be 200 minus 0.3 into 300. You can check calculation. Calculation is your part. If you will do the calculation, value of N will come 100 into 300 divided by 200 minus 0.3 into 300. It is coming 272.727 Newton. So it is the value of N. Now what examiner is asking? Examiner is asking about braking torque. So braking torque TB will be mu equivalent into N into radius of drum, and here I will use SI unit. So braking torque will come in Newton meter. Mu equivalent is 0.3 and we already calculated, it is coming 272.727, and R is radius of drum. So radius of drum in SI unit, that is meter, in 0.1 meter. So from this equation we will get in braking torque, and the value of braking torque is coming, it is coming 8.182, and since I have used SI unit, in SI unit, unit of torque is Newton meter, so it will come in Newton meter. So this is the value of braking torque, and examiner has asked about braking torque in Newton meter, and in Newton meter it is coming 8.182 Newton meter. Okay, 8.182. Since examiner has asked answer in correct up to 2 decimal place, therefore I have written answer in 2 decimal places. Okay. So student, we have discussed analysis of shoe brake. Now we will understand what is self-energizing brake and what is self-locking condition. Here I have written the definition of self-energizing brake and self-locking condition. But after reading this definition, I will explain various cases of shoe brake. And while I will explain various cases of shoe brake, during that explanation you will easily understand what is self-energizing brake and what is self-locking condition. Here I have written the definition of self-energizing brake. What is self-energizing brake? When friction reduces the braking effort, then that brake is known as self-energizing brake. Again I am repeating, what is self-energizing brake? When friction reduces, whenever friction is reducing the braking effort, that is value of P, then that brake is known as self-energizing brake. But you will understand what is self-energizing brake in more clear manner when we will discuss the various cases of shoe brake. Okay. Now, what is self-locking condition? If braking effort P will become 0 or negative, means braking effort is, if friction is reducing braking effort, then that brake is self-energizing brake. But just imagine friction is reducing that much value of effort, it is becoming 0 or negative. Then that special condition is known as self-locking condition, because in that condition brake will get automatically locked. Means whenever braking effort P is becoming 0 or negative, that condition is known as self-locking condition. For automobile or general case of brakes, self-locking condition is not a good thing. And if we want to avoid self-locking condition, then what we need to ensure, P must be greater than 0. Because if P is becoming 0 or negative, then that condition is known as self-locking condition. But you will understand these two things in more clear manner when we will discuss various cases of shoe brake. So after discussing various cases of shoe brake, again I will come in this definition. Just for this instant, just remember, whenever friction is reducing braking effort, then that brake is known as self-energizing brake. And if braking effort is becoming 0 or negative, then that condition is known as self-locking condition. If we want to avoid self-locking condition, then what we need to ensure, that P must be greater than 0. Okay. Now I am discussing various cases of shoe brake. This is the first case. What is this first case is saying? When line of action of friction force passes through fulcrum O and drum is rotating clockwise. Through this diagram, you need not to remember anything, only understand the concept. Here in this case, you can see friction force will act in this at this point, that point A, and friction force, direction of friction force will be horizontal, whether it is this side or this side, but it will be horizontal. So you can say that line of action of friction force is right now passing through fulcrum O. This is first case, and in this case we are discussing the case when drum is rotating clockwise. So what we will do for this case, we will find the expression or relation between P and N, that is braking effort, and N and friction force, and method is same. What we will do, first we will draw the FBD of drum and lever, and drum and lever both are we are considering that both are connected with this single contact point A, because we are imagining this whole contact region, we are replacing this whole contact region with single contact point A. Now first we will draw the FBD of drum. So in FBD of drum at point A, first normal force capital N will come, and its direction will be from point A towards center of drum. So if we will draw the direction of N, it will be like this. Now friction force will be perpendicular to N. It's okay. Now it says in the FBD of drum, the direction of friction force will be such that it will be opposite to the velocity of point A. So first we will find the direction of velocity of point A. Right now point A, drum is rotating clockwise. So at this instant, direction of velocity of point A will be this, and in the FBD of drum, friction will act opposite to the direction of velocity of A. Since direction of velocity of A this is this, friction force, direction of friction force will be this, and magnitude of friction force is mu E into N. Now we will draw the contact force at location A in the FBD of lever, and in FBD of lever, contact force at A will be equal and opposite of the contact force which are coming at point A in the FBD of drum. So in the FBD of drum at point A, N is acting downward. So in the FBD of lever at point A, normal force N will come upward. In the FBD of drum, friction force is coming in this direction. So in the FBD of lever, friction force will come in this direction. Now in the FBD of lever, what we will do, we will take net moment about fulcrum O is equal to 0, and it will be first we will find the direction of moment of effort P. I am taking clockwise as positive and anti-clockwise as negative. So direction of moment of force P about O will be P into perpendicular distance, which is B plus C, and its direction about O will be clockwise, and I am considering clockwise direction as positive. Now direction of moment due to force N, it will be N, its perpendicular distance from point O is B, and direction of moment is anti-clockwise. I am considering clockwise as positive and anti-clockwise as negative. Now friction force, the moment due to friction force is mu E into N, but right now its perpendicular distance from point O is 0, because line of action of friction force is passing through point O. Means can I say in this case the direct magnitude of moment due to friction force is 0, and since it is 0, we whether you use plus sign or minus sign, it will not matter. So it is net moment about fulcrum O, which is 0. So from this relation, braking effort P will be NB upon B plus C. Now this, you need not to remember this relation. Automatically whenever you will in the ability of lever, you will take write the equation of net moment about fulcrum equal to 0. Automatically this equation will come. But from this equation, can I conclude whether this brake is self-energizing brake or not? Yes, you can conclude. How? You can see what was self-energizing brake. If friction force, here friction force is mu e into n. If friction force is reducing braking effort, then that brake is self-energizing brake. So here you can see in the relation of P, friction force is not coming. Means friction force is neither in reducing the braking effort in this case, nor increasing the braking effort. Okay, means this brake is not a self-energizing brake, because to have self-energizing brake, friction should reduce the braking effort. Okay, it is also true, it is not increasing the braking effort, but it will not matter. For self-energizing brake, friction should reduce the braking effort, and here friction is not doing anything. If we will talk about with respect to braking effort, means here friction is not reducing braking effort, and since friction is not reducing braking effort, this brake is not a self-energizing brake. So first conclusion, you need not to remember this conclusion. If you want, you can remember, but you need to understand this. Since friction is not reducing the braking effort, therefore this brake is not a self-energizing brake. Since friction is not reducing braking effort, hence brake is not a self-energizing brake. Okay, now in short I will always write self-energizing brake as SEB, and for self-locking condition I will use SLC. So whenever I am writing SEB, it means self-energizing brake, and whenever I am writing SLC, it means self-locking condition. Okay, now can this brake can go in self-locking condition? No, this brake can never be go in self-locking condition, because what was self-locking condition? If P is becoming 0 or negative, then that brake will come under self-locking condition. But here from this relation you can see this portion is always positive, and here no negative term is coming. Means here braking effort can never become 0 or negative. Means this brake cannot be in self-locking condition. Okay, so if any brake is not self-energizing brake, you can also say that brake can never go in self-locking condition, because if brake is not self-energizing, means no part will reduce braking effort. If no part is reducing braking effort, means braking effort can never become 0 or negative, and if braking effort can never become 0 or negative, means that brake can never go in self-locking condition. So can I say this brake can never be in self-locking condition? Okay, what was the case? Line of action of friction force passes through fulcrum and drum is rotating clockwise. That case we have discussed. Okay, now second case we will discuss. In this case, again line of action of friction force passes through fulcrum O. At this point, friction force will act in horizontal direction, which is passing through fulcrum O, and drum is rotating anti-clockwise. In earlier case drum was rotating clockwise, but now in this case drum is rotating anti-clockwise. So we are discussing this case for anti-clockwise rotation of drum. Again, to do the analysis of this case, first we will draw the FBD of drum and lever. So again we are considering this drum and lever is connected with this single contact point A. First we will find contact force at A for the FBD of drum, then we will draw the FBD of lever. So first I am drawing the FBD of drum. In FBD of drum at point A, first we will draw normal force. I have already discussed the direction of normal force will be from point A towards center. So it will be like this. Now friction force. Friction force will be perpendicular to N, means it will be in this direction. And sense of friction force will be opposite to velocity of point A in the FBD of drum. So for that first we need to find the direction of velocity of point A. Since drum is rotating anti-clockwise, so the direction of velocity of point A will be this, and friction force in FBD of drum will be opposite to this velocity. Means can I say in this case, since velocity is in this direction, friction force will be in this direction. So it is the direction of friction force. Now we will find contact force at A for the FBD of lever. Okay, and it will be opposite to the contact force which are coming in the FBD of drum. So right now in the FBD of drum at point A, N is acting in downward direction. So in the FBD of lever, N will be in upward direction. Friction force is acting in this direction. So in the ability of lever, friction force will be in direction. After that, in the ability of lever, we will take net moment about fulcrum O equal to 0 in the ability of lever. Okay. Now, first we'll take the moment of effort P. It is P, its perpendicular distance from fulcrum is B plus C. So moment will be P into B plus C. Now direction. The direction of moment due to effort P about O is clockwise. We are considering clockwise direction as positive and anti-clockwise as negative. Now we'll take the moment of N. It is N, its perpendicular distance from O is B. So moment will be N into B. Now direction of movement due to this force N about O is anti-clockwise. We are considering clockwise as positive and anti-clockwise as negative. Now moment of friction force. Again friction force is mu E into N. But right now again is this perpendicular distance from point A is 0. Why? Because line of action of friction is passing through fulcrum O. So right now moment of friction force is 0. So we need not to write this. Okay. So it is net moment about fulcrum O which is equal to 0. From this equation, if you will find the relation of effort P, it will be NB upon B plus C. Again, you need not to remember this. From this ability, you can easily find this relation. But from this formula of or expression of effort P, what we can conclude? Can we conclude here that this brake is not self-energizing brake? Why, sir? Because again, in this relation, no friction term is coming, which is trying to reduce the braking effort. And since here friction is not reducing the braking effort, means again this brake is not a self-energizing brake. Means again same conclusion. Since friction is not reducing braking effort, therefore this brake means when line of action of friction is passing through fulcrum and drum is rotating anti-clockwise. Therefore this brake is not a self-energizing brake. Okay. Now if any brake is not a self-energizing brake, then that brake can never be go in self-locking condition. Why? Because to be in self-locking condition, P must be either equal to 0 or less than 0. But here from this relation you can say that P can never become 0 or negative because it will always be positive. And since P can never become 0 or negative, means here this brake can never be in self-locking condition. Means if any brake is not a self-energizing brake, means that brake can never be in self-locking condition. So this brake can never be in self-locking condition. Okay. Now if you want to remember this case, can I conclude whenever line of friction is passing through fulcrum O, whether drum is rotating clockwise or anti-clockwise, it will never be that brake never be self-energizing brake. Why, sir? Because when line of action of friction was passing through fulcrum O and drum was rotating clockwise, in that case also we have concluded that brake is not a self-energizing brake. Similarly, again when line of action of friction is passing through fulcrum and drum is rotating anti-clockwise, in that case also we have concluded that drum brake is not a self-energizing brake. Means can I conclude whether drum is rotating clockwise or anti-clockwise, if line of action of friction is passing through fulcrum, but it should satisfy, because we have already right now we have already discussed the case when line of action of friction is passing through fulcrum. So if line of action of friction is passing through fulcrum O, then that brake can never be self-energizing brake, whether it is rotating clockwise or anti-clockwise. So this is general conclusion. Means whenever this is general conclusion, whenever in shoe brake, we are discussing right now shoe brake only, whenever line of action of friction is passing through fulcrum O, that brake can never be self-energizing brake. Whether drum is rotating clockwise, that brake can never be will not be self-energizing brake, whether drum is rotating clockwise or anti-clockwise. But line of action of friction should pass through fulcrum. If you want to remember this, you can remember. Okay. And if brake is not a self-energizing brake, then that brake can never go in self-locking condition, because in that case P can never become 0 or negative. Means, can I say, in that case the brake can never be in self-locking condition. Means P will always be greater than 0. It will never become 0 or negative. Okay. So if you want, for this case you can remember this conclusion. But now next case which I am going to discuss is important. When line of action of friction is not passing through fulcrum. Okay. That case is very, very important. So the third case is line of action of friction force is above fulcrum. If line of action of friction is not passing through fulcrum, it will be either above O or it will be either or below O. So right now we are discussing the case when line of action of friction is above fulcrum. At this point friction force will come. This is point A. At this point friction force will come in horizontal direction. So it is the line of action of friction which is above fulcrum O. And right now we are discussing the case when drum is rotating clockwise. So this case is line of action of friction is above fulcrum O and drum is rotating clockwise. You need not to remember this. Only understand the process and what conclusion is coming. You need not to remember or you need not to mug up anything. Okay, you need to understand. Now drum is rotating clockwise. For that case, this case again we will derive the expression between P, N and friction force. For that first we will draw the ability of drum and lever. To draw that ability, we are considering this lever, shoe of the lever, and drum is connected with single contact point, that is A. Now first we will draw the ability of drum. In ability of drum, first we will draw the normal force capital N. The direction of normal force in the ability of drum will always be from point A towards center. So it will be like this. So it is normal force. Now friction force will be perpendicular to N. So right now normal force is vertical, so friction force will be horizontal. Now in this direction, the sense of friction force will be such that it should be opposite to the direction of velocity of A, if we are drawing the friction force in the ability of drum. So first we need to find the direction of velocity of A. Since drum is rotating clockwise, so at this instant direction of velocity of A will be this, and friction force in the ability of drum will be opposite to velocity of A. Since this is the direction of velocity of A, friction force will be in this direction. So it is the direction of friction force. Now we will find the contact force in the ability of lever. It will be opposite to the contact force which are coming in the ability of drum. So in ability of drum at point A, direction of N is this. So in ability of lever, N will be opposite, means this. In the ability of drum, direction of friction force is this. So in ability of lever, it will be equal and opposite, means direction of friction force will be this. Now in the ability of lever, we will take net moment about fulcrum O equal to 0. Automatically we will get the relation between P, N and friction force. It will be the moment of effort P about fulcrum O. It will be P. Its perpendicular distance from O is B plus C. Now direction of movement about O is clockwise. I am taking clockwise direction as positive. Now direction of movement due to force N, it will be N. Its perpendicular distance from O is B. Now movement about O is anti-clockwise. I am considering clockwise as positive, so anti-clockwise as negative. Now movement due to friction force, it will be friction force is mu E into N. Its perpendicular distance from point O is A. So movement is this. Its direction about fulcrum O is clockwise, and I am taking clockwise direction as positive. Okay. This is net moment around fulcrum O, which is equal to 0. From this equation, if you will find the expression of P, it will come NB. Be careful with sign. This plus will come this side, it will become minus mu E into Na divided by B plus C. Again, you need not to remember this relation. Okay, but what conclusion I am making, understand that. Here you can see friction force is coming in the relation of P. And now visualize whether friction is reducing braking effort or increasing. Here you can see friction is coming with minus sign in this relation. Means, can I say in this case friction will reduce braking effort? And since friction is reducing braking effort, means can I say in this case brake is self-energizing brake? Which case we were discussing? Line of action of friction is above fulcrum O and drum is rotating clockwise. Don't make any conclusion. Means don't say suppose whenever line of action of friction will be above fulcrum O, brake will be self-energizing. No. because here line of action of friction is above fulcrum O, along with that drum is rotating clockwise. Right now we have not discussed this case for anti-clockwise rotation of drum. So don't remember anything, just understand the concept. For this case, if examiner is asking whether brake is self-energizing or not, just derive this relation. After that, see whether friction is reducing braking effort or not. So right now what we have concluded by looking this relation, friction is reducing braking effort. Means in this case, brake is self-energizing brake. So can I say in this case, since friction is reducing braking effort, therefore this brake means when line of action of friction is above fulcrum O and drum is rotating clockwise. Okay, this brake is self-energizing brake. Now this is about self-energizing. This is self-energizing brake. Now what about self-locking? So you can see here this part is coming with plus sign, this part is coming with minus sign. Means if the weightage of this part is more, P will be positive. If weightage of this part is equal to this or more than this, then P will be either 0 or negative. And if P is greater than 0, then brake will not be in self-locking condition. But if P is becoming 0 or negative, brake will go in self-locking condition. Means can I say in this case, brake can be in self-locking condition also, and brake cannot be in self-locking condition also, because if P is less than 0 or equal to 0, it will be in self-locking condition, and that case is possible when value of this is equal to this or value of this is more than this. And if P is greater than 0, then brake will not be in self-locking condition, and this is also possible when NB is more than this. Means here if brake is self-energizing brake, in that case can I say brake can be in self-locking condition also, and brake cannot be in self-locking condition also. For that we need to check whether P is greater than 0 or less than equal to 0. If P is greater than 0, brake will not be in self-locking condition. If P is less than equal to 0, brake will be in self-locking condition. Okay, means when brake is self-energizing brake, in that case for self-locking we need to check whether if P is less than equal to 0, it will be in self-locking condition. If it is greater than 0, not equal to 0, greater than 0, then it will not be in self-locking condition. So for that what you can do, here you have concluded that both cases possible. So for that, first find the case to avoid self-locking condition. Always I will find the case to avoid self-locking condition. Okay, and whatever condition is coming to avoid self-locking condition, if that condition is satisfying, then brake will not be in self-locking condition. And if that condition is not satisfying, means automatically brake will be in self-locking condition. So if you have found the relation to avoid self-locking condition, means the opposite of that relation will be the relation which will ensure that brake is in self-locking condition. So I will always find the to avoid self-locking condition, because for automobile point of view this condition is not a good thing. Okay, so to avoid self-locking condition, what we need to ensure, P must be greater than 0. It should not be equal to 0 also, because if it is equal to 0 means it is self-locking condition. Now to ensure P is greater than 0, what we need to ensure, this top part, that is NB minus mu E NA, should be greater than 0. Means to avoid self-locking, NB minus mu E NA should be greater than 0. Okay, so from this relation if you will find, N and N will get cancelled, B should be greater than mu E into A. Means in this case, if B is greater than mu E into A, means brake will not go in self-locking condition. Now if examiner is asking when is this brake will be in self-locking condition, it is the condition to avoid self-locking. When brake will be in self-locking condition, when P is equal to 0 or less than 0. So find the expression for that. But if you find this expression, you can easily write this. How? If this condition is satisfying, means brake will not be in self-locking condition. Means if you want brake should be in self-locking condition, means this condition not satisfy. And why opposite of this condition is, here B is coming greater than mu A. So to be in self-locking condition, either B should be equal to mu EA or B should be less than mu EA. Because if B is greater than this, P will be greater than 0, and if B is satisfying this relation, P will be either equal to 0 or less than 0. And P is less than 0 equal to 0 means brake will be in self-locking condition. Means for this case conclusion are, you need not to remember, only understand. Since first we have derived this expression and we have concluded friction is reducing braking effort, therefore this brake is self-energizing brake. Now if brake is self-energizing brake, it can be in self-locking condition also and it cannot be in self-locking condition also. So if we want to find the relation to avoid self-locking condition, so what we need to ensure, P must be greater than 0. And from this relation, to ensure P must be greater than 0, NB must minus mu E NA must be greater than 0. To satisfy this, B must be greater than mu E into A. So if this equation is satisfying, brake will not be in self-locking condition. So this is the condition to avoid self-locking. And if we want that brake should be in self-locking condition, this relation should satisfy. Okay. Now again I will say, don't remember this relation. First derive this. If brake is self-energizing, then find this relation to avoid P must be greater than 0. Automatically this will come. To be in self-locking condition, this condition should not satisfy. So why I am saying don't remember this? Because now I will discuss next case. In that case, you will find that brake is not a self-energizing. And if brake is not a self-energizing, it will never go in self-locking condition. We need not to satisfy anything. That's why I am saying don't remember this. Understand the concept. How? Why? Now this is the next case. Again in this case you can see line of action of friction force is above fulcrum. Earlier case also, in earlier case also line of action of friction was above fulcrum. But here difference is, in earlier case drum was rotating clockwise, here drum is rotating anti-clockwise. What changes will come now? So again line of action of friction is above fulcrum, but instead of clockwise now drum is rotating anti-clockwise. So to do the analysis of this case, again we will draw the FBD of drum and lever. Drum is rotating anti-clockwise. First we will draw the FBD of drum. This is the contact point A. In this contact point normal force capital N will come. Now direction of normal force will be in the FBD of drum from point A towards center. So this is normal force N. Friction will be perpendicular to N, so it will be in this direction. Now in this direction the sense of friction will be such that it should be opposite to the direction of velocity of A. Since drum is rotating anti-clockwise, so at this instant direction of velocity of A will be this, and friction should be opposite to this. So friction will act in this direction. Now we'll draw this contact force at point A in the FBD of lever, which will be opposite to this direction. Now in FBD of drum, N is coming downward, so here N will be upward. In FBD of drum, friction is coming in this direction, so here friction will be in this direction. After drawing this FBD, in the FBD of lever, we will take net moment about fulcrum O equal to 0, and this will come. The moment of effort P about O, it will be P. Its perpendicular distance from O is B plus C. Now direction of effort, moment of effort P about O is clockwise, and I am considering clockwise direction as positive and anti-clockwise as negative. Now moment of this normal force N, it is N. Its perpendicular distance from O is B. Now direction of movement about O is anti-clockwise. I am taking clockwise as positive, so I will take anti-clockwise as negative. Now friction force. Friction force is mu E into N. Its moment. So its perpendicular distance from point A is A. So moment due to friction force will be this. Now its direction. The direction of movement due to friction force about O. See carefully. It is anti-clockwise. And I am taking anti-clockwise direction as negative. I am equating this equal to with 0. So from this, if you will find the relation of P, it will come and B, and this minus will come this side, it will become plus mu E NA divided by B plus C. Now from this, again you need not to remember this relation, but from this relation what conclusion you can make? Here you can see that friction is coming with plus sign, means here friction is not reducing braking effort. Instead of that, friction is increasing braking effort. That is different thing. But for self-energizing brake, we need to see whether friction is reducing braking effort or not. So here can I conclude that in this case, means when line of action of friction force is above fulcrum O and drum is rotating anti-clockwise, in that case friction is not reducing braking effort. And since friction is not reducing braking effort, means can I say in this case brake will not be self-energizing brake. So in this case, since friction is not reducing braking effort, therefore brake is not a self-energizing brake. Means in this same case, when drum was rotating clockwise, brake was self-energizing, But when drum is rotating anti-clockwise, brake is not a self-energizing brake. Means whenever line of action of friction is above fulcrum O, and if drum is rotating clockwise, brake will be self-energizing, and if it is rotating anti-clockwise, brake will not be self-energizing. But don't memorize this, because in exam, if you will memorize this, you will get confused. Find the relation between P, N and mu N. From this relation, if friction is reducing braking effort, means it will be self-energizing. If it is not reducing, it will not be self-energizing. Very simple. Why to remember? Okay. Now, if brake is not self-energizing, means that brake can never go in self-locking condition. Why? Because from this relation, it is positive, it will also always positive. Means can I say in this case, P will always be greater than 0? Means brake will never go in self-locking condition. That's why I told you in earlier case, don't remember this. If B is greater than mu A, then it will not be in self-locking. If B is less than equal to mu A, it will be in self-locking. Because here this relation is coming. But here what conclusion is coming? That this brake can never be going in self-locking condition. Because in this case, P can never become 0 or negative. So can I say in this case, brake will never be in self-locking condition. Okay, so it is one of the case. Now we'll discuss next case. What is this case? Line of action of friction is below fulcrum O. In earlier case, line of action of friction was above fulcrum O. Here line of action of friction is below fulcrum O, and drum is rotating clockwise. Again, to do the analysis of this case, we'll draw the FBD of drum and lever. So it is here I am drawing the FBD of drum and lever. First I will draw the FBD of drum. So first we'll draw contact force N. The contact force L, direction of contact force N will be from point A towards center, so it will be this. Now friction force will be perpendicular to this. Now sense of friction force will be opposite to velocity of A in the FBD of drum. Right now drum is rotating clockwise, so at this instant direction of velocity of A will be this. And friction force in the FBD of drum will be opposite to velocity of A. Right now velocity of A, direction of velocity of A is this, so friction force will be this. Now we will draw the contact force at A in the FBD of lever. It will be opposite to these forces. Right now in FBD of drum, N is coming downward. So in FBD of lever at point A, N will come upward. Friction force is coming in this direction. So here friction force will come in this direction. Now in this FBD of lever, we will take summation of moment about fulcrum O equal to 0. It will be the moment of effort P about O. It is P. Its perpendicular distance from O is B plus C. Now direction of movement is clockwise. I am taking clockwise direction as positive. Now and its perpendicular distance from fulcrum O is B. Direction of movement is anti-clockwise. I am taking clockwise as plus and anti-clockwise as minus. Now friction force. Friction force is mu E into N. Its perpendicular distance from fulcrum O is A. So movement will be into A. Now direction. Here direction of movement due to friction force about O is anti-clockwise. See carefully. And I am taking anti-clockwise direction as negative. Now net movement about fulcrum O equal to 0. From this equation, if you will find the expression of P, it will come NB plus mu E into NA upon B plus C. Again, we need not to remember this relation. But from this relation, for this case, what conclusion we can make? See whether friction is reducing braking effort or not. So here you can see friction is increasing the braking effort. It is increasing, means friction is not reducing the braking effort. And since friction is not reducing the braking effort, can I say in this case when line of action of friction is below fulcrum O and drum is rotating clockwise, in this case brake is not a self-energizing brake. So can I conclude, since friction is not reducing braking effort, therefore brake is not a self-energizing brake. This is first conclusion. Now since this brake is not self-energizing brake, this brake can never go in self-locking condition, because from this relation you can see that P can never become 0 or negative. So can I say this brake can never be in self-locking condition. Means if brake is not self-energizing, that conclusion is very simple. Then that brake can never be in self-locking condition. Okay. Now, in this same case, we'll discuss another case. Means again, we'll discuss next case. In that case, also line of friction will be low fulcrum O, but instead of clockwise rotating drum, we'll take the case when drum is rotating anti-clockwise. Means next case, and it is the last case, is when line of action of friction is below fulcrum O and drum is rotating anti-clockwise. After discussing this, I will make some interesting conclusion. If you want, you can remember those interesting conclusions. If you want, it is not necessary, but if you want. But before that, first we will close this next case, that is case number 6. Line of action of friction is below fulcrum O and drum is rotating anti-clockwise. Again, to do the analysis of this case, we will draw the ABD of drum and lever. First I am drawing the ABD of drum. Drum is rotating anti-clockwise. Okay. Now first I will draw contact force N. It directs in the ABD of drum. Contact force N will always be from point A towards center, means it will be like this. Now friction force will be perpendicular to N. Now in this direction, sense of friction force will be such that it should be opposite to velocity of A whenever we are drawing friction force in ABD of drum. So at this instant, since drum is rotating anti-clockwise, so direction of velocity of A will be this, and friction force will be opposite to this direction, means it will be in this direction. Now we will draw this contact force in the ABD of lever, and in the ABD of lever at point A, this contact force will be equal and opposite to these directions. So for contact force N, here N is coming downward, so in lever at point A, N will come upward. Here friction is coming in this direction, so here friction will come in this direction. After this, in the ABD of lever, we'll take net moment about fulcrum O equal to 0. It will come first moment of P about, this is fulcrum O. Moment of P about fulcrum O is P. Its perpendicular distance from O is B plus C. Direction is clockwise. I am taking clockwise direction as positive. Now moment due to N, it is N. Its perpendicular distance from O is B. Direction is anti-clockwise. I am taking anti-clockwise as negative. Moment of friction force, it will be mu E into N. Its perpendicular distance from O is A. Now direction of movement due to friction is clockwise. Check carefully, clockwise, and I am taking right now clockwise direction as positive, and I am equating this with 0. So P will be this minus will come this side, it will become plus. This plus will come this side, minus mu E Na upon B plus C. Now what conclusion we can make? Now see this relation carefully. In this relation, friction is reducing braking effort because it is coming with minus sign. Means can I say this brake is self-energizing brake? Which brake? When line of action of friction is below fulcrum O and drum is rotating anti-clockwise. When in this case drum was rotating clockwise, what we have concluded, brake was not self-energizing. But in the same case, when drum is coming rotating anti-clockwise, what conclusion we have made? It is self-energizing brake because friction is reducing braking effort. So since in this case friction is reducing braking effort, therefore this brake is self-energizing brake. Now if brake is self-energizing brake, in that case that brake can also go in self-locking condition, and if P is becoming 0 or negative, or brake cannot be in self-locking condition also if P is greater than 0. Here you can see also, if this is more than this, P will be greater than 0, this brake will not be in self-locking condition. If this term is equal to this or this term is more than this, then P will become 0 or negative, means brake will be in self-locking condition. So here both cases are possible. So if we want to find the case when brake is not in self-locking condition, means if I want to find the case when self-locking condition is not occurring, means we want to find the condition to avoid self-locking condition. And if we want to avoid self-locking condition, what we need to ensure? P must be greater than 0. Now to ensure P must be greater than 0, this term should be greater than 0, means NB minus mu E Na must be greater than 0. Okay, so from this conclusion will come B must be greater than mu E A. So if this condition is satisfying for this case, again you need not to remember this, after deriving this you can easily find this. So if you are satisfying this condition, brake will not be in self-locking condition. Similarly, if you want to find the condition when brake is in self-locking condition, so if this condition is satisfying, means brake is not in self-locking condition, means brake will be in self-locking condition when this condition is not satisfying. When this condition will not satisfy, opposite to this condition, the condition which is opposite to this is B. Here B is greater than, so here B will be less than equal to mu EA. And if this condition is satisfying, brake will be in self-locking condition for this case. Because if this condition is satisfying, then P will be either equal to 0 or less than 0. So here, in this case, brake is a self-energizing brake because friction is reducing braking effort. In this case, if I want brake should not go in self-locking condition, means P should be greater than 0. So we need to satisfy this equation. If this equation is not satisfying, means B is less than equal to mu E into A, brake will be in self-locking condition, that is P will become 0 or negative. Now, if you understand all this case, what conclusion we can make? Here, in first point, I have written one important conclusion. What is this conclusion? Read carefully. If direction of moment of friction force and braking effort about fulcrum O, take about fulcrum O. You cannot, if you want to remember this conclusion, you have to take moment about fulcrum O and only see the direction. If direction of moment of friction force, here this friction force is coming and here braking effort is coming about O in the body of lever is same, this is the key point, then that brake will act as self-energizing brake. If you want to remember this, that you can remember. Okay, but if you don't want to remember, by deriving the expression of P, you can easily make the conclusion brake is self-energizing or not. But if you want to remember, if in the body of lever in shoe brake, this conclusion is for shoe brake, direction of moment of effort P and direction of moment of friction force, only see the direction of moment of effort P and friction force. If both direction is same, then that brake will be self-energizing brake. And if that both direction are not same, means the case, if direction of moment of friction force and effort P is same, brake is self-energizing. Otherwise, brake will not be self-energizing. Like I am going in reverse order. In this sixth case, see, in the body of lever, what is the direction of moment? Here I am writing moment about O, only the moment about O for effort P and for friction force. What is the direction of moment of effort P about O? See the direction of moment, not force. Due to effort P, the direction of moment about O is clockwise. Now, what is the direction of friction force about fulcrum O? In the body of lever, don't see this, see this. The direction of moment of friction force about O is also clockwise. So here you can see the direction of moment of both effort P and friction about O is same. And if both direction is same, means brake will be self-energizing. And same conclusion we have made. Since friction is reducing braking effort, this brake is self-energizing. Same. In fifth case brake was not self-energizing. You can again check by this method also. From this relation we have make the conclusion that brake is not self-energizing. By this method also we will conclude. See the direction of moment about O for effort P and friction force. You need to see the direction of moment. What is the direction of moment of effort P about O? It is clockwise. Yes, sir. What is the direction of moment of friction force about O? It is anti-clockwise. Both are not same. So if both direction is same, brake is self-energizing. And other case, so this case is not satisfying. No? Both direction is not same. Means in this case, brake will not be self-energizing brake. And same conclusion we have made. This brake is not a self-energizing brake. Similarly, in fourth case also you can say direction of moment about fulcrum O for effort P and for friction force. Here you can see direction of moment of effort P about O is clockwise. Okay. Now direction of moment of friction force about O is anti-clockwise. Check carefully. Both direction are not same, means brake is not self-energizing. Same conclusion we have made. Then we have discussed this case 3. In that we have made conclusion brake is self-energizing by this relation. Now I am using this method, direction of moment of effort P about fulcrum and friction force, moment of friction force about fulcrum. Direction of moment of effort B about fulcrum is clockwise. Direction of moment of this friction force in the body of lever about fulcrum O is also clockwise. Means again both direction is same. And if both direction is same, means this brake is self-energizing. Same conclusion we have made. In case 2, when line of action was passes through fulcrum, for this case, but you can directly remember. If line of action of friction is passing through fulcrum O, brake can never be self-energizing brake. But again, if you want to check by this method also, you can see the direction of movement of effort P about fulcrum is clockwise, and the friction force movement about fulcrum is zero. Is zero means its direction will also not come, means both direction is not same. For self-energizing, the direction of movement of effort P and friction force, direction of movement of friction force about fulcrum should be same. Otherwise, brake will not be self-energizing. So this case is coming in otherwise case. Why? Because the friction here movement of friction force about fulcrum is zero. Means this brake is not self-energizing. Same conclusion we have made. But for this case, when line of action of friction is passing through fulcrum O, you can directly remember whether drum is rotating clockwise or anti-clockwise, brake will never be self-energizing. Brake will never be self-energizing. For this case, when line of action of friction is not passing through fulcrum O, either make conclusion by deriving this equation or just see the moment of effort P and friction force. If direction of movement of effort P and friction force about fulcrum O in the ability of lever are same, then brake will be self-energizing brake. Otherwise, brake will not be self-energizing brake. So this is the first very important point. Okay. Now second point, if brake is not a self-energizing brake, then that brake can never be in self-locking condition. Same conclusion. This brake was self-energizing, so it can be in self-locking condition. But this brake was not self-energizing, so it can never be in self-locking condition. Okay. So if brake is not a self-energizing brake, means that brake can never be in self-locking condition. Okay. You need not to find any relation, because in that case brake never be in self-locking condition. We need not to satisfy any condition. But if brake is self-energizing brake, we are talking about shoe brake, then that brake may or may not be in self-locking condition. Both cases are possible. Brake will be in self-locking condition if P is less than equal to 0, and brake will not be in self-locking if P is greater than 0. So if examiner is asking what is the condition to avoid self-locking condition, to avoid self-locking, if he is asking in this case when brake is not self-energizing, so we'll say in that case brake will never be in self-locking condition. But if examiner is asking in this case, and examiner is saying it what condition brake will not be in self-locking condition, means examiner is asking the condition to avoid self-locking condition. So first find the relation between P and mu n, and this brake is self-energizing, means it can be in self-locking also or it cannot be in self-locking. So to avoid self-locking, P must be greater than 0, and to ensure P greater than 0, find the relation which is coming. If we are satisfying this condition, brake will not be in self-locking condition, and if this condition is not satisfying, brake will be in self-locking condition. So if examiner is asking condition to avoid self-locking, find the relation which will ensure P is greater than 0. If that condition is satisfying, it will not be in self-locking. If it is not satisfying, it will go in self-locking condition. Okay. Based on this discussion, we will discuss some questions. What this question is saying, it is MCQ. In this question, this distance is given, this distance is given, this is the direction of braking effort, drum is rotating clockwise. This distance is A, it is not given. But line of action of friction, you can see it is above fulcrum. Now, coefficient of friction between the shoe and drum is given, that is mu, which is 0.25. Which one of the following option is correct to avoid self-locking? So examiner is asking condition to avoid self-locking. Okay, where option is saying brake will never be in self-locking. This can case also come. If brake is not self-energizing, that it can never be in self-locking. But if it is self-energizing, then we need to find the relation to avoid self-locking, and we have to find which options are correct. Here mu is given. Examiner has not mentioned whether this brake is short shoe or long shoe, and along with that block angle is also not given. And I already told you, if block angle is not given and examiner is not mentioned, then consider that brake as short shoe brake. And if it is short shoe brake, mu equivalent will be equal to. Now to the analysis of those case, we will draw the ability of drum and lever first. Okay. Now we will draw the ability of drum and lever. Suppose we will replace this whole contact region with single contact point A, which is midpoint of this region. So this is point A. So first we will find the contact force in the ability of drum at location A. It will be first normal force capital N. It will be that in the ability of drum, direction of normal force will always be from point A towards center. So it will be the direction of normal force N in ability of drum. Now friction force, which will be perpendicular to N. Now sense of friction force in the ability of drum will be opposite to direction of velocity of A. Since drum is rotating clockwise, the direction of velocity of A will be this. So friction force will be opposite to this, means this is the direction of friction force. Now we will find the direction of this contact force for FBD of lever. It will be opposite to this. So N is coming downward in FBD of drum. So in FBD of lever, N will be upward. Friction force is coming in this direction. So in FBD of lever, friction force will be in this direction. And it is the direction of braking effort. Okay. Now if you want to only check, right, suppose here examiner asking to condition to avoid self-locking. But if examiner is only asking whether this brake is self-energizing or not, so you need not to derive, only see the direction. Here direction of movement of effort P about O is clockwise, clockwise. Now direction of movement of friction force about O is also clockwise, and since both direction are same in FBD of lever, means this brake is self-energizing. And if it is self-energizing, it will be in self-locking condition if P is less than equal to 0. It will not be in self-locking condition if P is greater than 0. Examiner asking condition to avoid self-locking. For that, first find the relation between P and N mu N. For that, in this equation, in this FBD of lever, we will take net moment about fulcrum O equal to 0. This relation will come. Direction of movement of effort P about O. It is P, its distance from O is 500. Now movement is clockwise. I am taking clockwise as positive. Now direction of movement of force N, it is N, its perpendicular distance from O is 100. Direction is anti-clockwise. I am taking clockwise plus, anti-clockwise minus. Now friction force movement, friction force is mu E into N, its perpendicular distance from O is A. So it is A. Now direction of movement about O is clockwise. I am taking clockwise direction as positive, equal to 0. So P will be equal to 100 N minus mu equivalent. Mu equivalent is given in the question, it is equal to mu, which is 0.25. So minus 0.25 NA upon 500. And here this is friction force, which is reducing the braking effort. And since friction is reducing braking effort, means this brake is self-energizing. Okay. And since it is self-energizing, here it can be in self-locking also, and it cannot be in self-locking. If P is less than equal to 0, it will not be in self-locking. If P is greater than 0, it will be in self-locking. Examiner asking condition to avoid self-locking. So in this case, to avoid self-locking condition, what we need to ensure? P must be greater than 0. For that, this top part should be greater than 0. That is 100 N minus 0.25 Na must be greater than 0. So N will get common and will go this side. So it will come 100 should be greater than 0.25 A. And if you will find the 100 divided by 0.25, it will come 400. 400 should be greater than A. So in A side, less than sign is coming. So can I say in this case, A should be or must be less than 400. And since we have taken distance in mm, it will also come in mm. So can I say in this case, to avoid self-locking, A must be less than 400. It should also not be equal to 400. It should be less than 400. So if A is less than 400 mm, self-locking condition, brake will not be in self-locking condition. And if this condition is not satisfying, means either A is equal to 400 or greater than 400, in that case brake will be in self-locking condition. So since examiner asking condition to avoid self-locking, for that we need to satisfy this condition, that is A must be less than 400. Which option is correct? Option B. Okay. But suppose for some other question, suppose in this case, instead of clockwise, if drum was rotating, is rotating anti-clockwise. It is your homework. But if drum will rotate anti-clockwise, then conclusion will be brake will not be self-energizing. And if brake is not self-energizing, brake can never go in self-locking condition. In that case, option A will be correct. But right now, for this question, option B is correct. Okay. So this is the question. Now we will discuss what is maximum pressure in shoe brake. So we already discussed in shoe brake, pressure will induce between the shoe and drum, and it will be maximum at midpoint of the contact region, that is point A, which we are denoting in the FBD. Now what will be the expression of maximum pressure? So suppose this is shoe of our shoe brake. In this shoe brake, this dimension I am denoting as L, which is known as length of the shoe. This dimension is known as width of the shoe, and this is radius of drum R. The drum which is connected here, the radius of that drum is R. and this is angle of contact or block angle. Now, if the shoe is short shoe, to find the relation of maximum pressure in shoe brake, we need to see whether the shoe is short shoe or long shoe. So if the brake is short shoe brake and shoe is short shoe, in that case the expression of maximum pressure is capital N, which is normal force, divided by W into L. Okay, so it is the relation of maximum pressure for short shoe. Simple, it is very, you need to remember this relation. I am not going on derivation. Maximum pressure will be capital N upon W into L. Okay, but for long shoe brake, long shoe means 2 theta is more than pi by 4. Generally question will come from short shoe brake, but if question is coming from long shoe brake, the relation for maximum pressure is N upon, instead of W, here we will use this distance. This distance is R into 2 theta, because any arc length is will be R into radius into angle. So instead of W, R into 2 theta will come, along with that L will come as it is. So it is the relation of maximum pressure for short shoe, maximum pressure for long shoe. Generally question will come from short shoe. Okay. With respect to this relation, I am discussing one question. What this question is saying: a short shoe brake with a torque capacity of 250 Newton meter. So braking torque capacity is given. It is 250 Newton meter. Is shown in figure. Coefficient of friction is 0, mu is 0.3, and since it is short shoe brake, mu equivalent will be equal to mu. Yes sir. Radius of drum is given, that is R. It is 200 mm. In meter it will be 0.2 meter. Length of the block is twice of its width. What question is saying? Length of the block, that is L, is twice of its width. I am denoting width as W, so it is twice of width, that is L is equal to 2 times of W. If permissible intensity of pressure between the block and drum is 1 Newton per mm square, means limiting pressure is given. Suppose I am denoting permissible pressure as PP. P for pressure, this P is for permissible. It is 1 Newton per mm square. It means, can I say, in this short shoe brake, maximum pressure should either be equal to 1 or less than 1, because it is permissible pressure. And to find limiting value, we will equate maximum pressure with permissible to find the limiting value. Then examiner is saying what will be the length of block, means limiting length of the block, examiner is asking. Okay, and relation between length and W is given. For that, first we will find the maximum pressure, and maximum pressure, relation of maximum pressure, that should be less than equal to 1. To find limiting value, we will equate it with 1. Okay, now this brake is given. I am drawing the free body diagram of FBD of drum and lever. But here in this question, braking torque is given. Can, by using the braking torque, we can find the relation of N? Yes sir. Means in this question you need not to draw the FBD of drum and lever. If required, draw, but here you don't require. Why sir? Here only objective is to find the L, and what is will be P max is given. It should be less than equal to 1. To find limiting value, we will create this one. And what is the expression of P max? Sir, expression of P max for short shoe brake is N upon WL. Now relation between N and W is also given. So if you will equate this relation with 1, the L into W will come, and L is equal to twice of W. If you use this relation, you can find whether either W or L if you have find the value of N. Means to use this relation, first we need to find the value of N, and N we can calculate by using this braking torque value, because braking torque is given in the question, and formula to calculate braking torque is mu equivalent into N into radius of drum. Braking torque is given, mu equivalent is given, radius of drum is given, means we can find the value of N. And if we after finding the value of N, by equating this maximum pressure with 1, we can find L and W both. Means to solve this question, we need not to draw this FBD of drum and lever. If you want, you can draw, but we don't require to draw. Okay, so here in this question, braking torque is given TB, which is 250 Newton meter, and braking torque is nothing but mu equivalent into N into radius of drum. It is 250. In this question, mu equivalent is 0.3 into N into radius of drum is 0.2. So from this equation we can calculate value of N. How much it is coming? It is coming 250 divided by 0.3 divided by 0.2. It is coming value of N 4166.667 Newton. Okay. Now P max is equal to capital N upon WL, which must be less than equal to 1 Newton per mm square. For to find limiting value, we will equate this with N, with 1. So it will be N upon WL equal to 1. Now N is 41. Okay. Pressure we are taking in Newton per mm square, so we'll take N in Newton and WL, that is this area, in mm square. Okay. So N in Newton is 4166.667 upon W, and length is twice of W, so we can replace L by W. So from, and we'll equate this, L is twice of W. From this equation we'll get the value of W, and since pressure is in Newton per mm square, W will come in mm. And how much it is coming? The value of W, it is coming 45.643 mm. So it is the limiting value of W. Examiner is asking length of shoe, that is L, which is twice of W. So L will come into 2, it is coming 91.287 mm. Okay. So for this question, limiting value of length of shoe is 91.287. Okay. So it is the solution of this question. Okay. So student, we have discussed shoe brake. Now we will start the discussion of next brake, that is band brake. It is also very important. Okay. Now in band brake, we will discuss two type of brake: simple band brake and differential band brake. Whenever question of band brake is coming here, in that case you will find in the drum we have wrapped a band. This is known as band, and there will be friction lining in the band. On due to that friction lining, there will be high coefficient of friction between the drum and this band, and due to this friction, braking torque will induce in the drum. Okay. So here, instead of using shoe, we are using this band to apply brake, to get braking action in the drum. Now this band brake, whenever in this drum we have wrapped a band, then that brake is known as band brake. It is very simple. Now this band brake is further classified as simple band brake and differential band brake. Just see this diagram. What we will do, this both side of this band will be attached to this lever. This lever is known as brake lever. Same lever. In shoe brake there was a lever in which we are applying braking effort. Similarly here also it is a lever in which we are applying braking effort. And in the lever, the point at which this lever is hinged, like this lever is hinged at this location, which is known as O, which is known as fulcrum. Again in this diagram, this lever is hinged at this location. See where lever is hinged, that point is known as fulcrum, which I am denoting as O. So O is nothing but fulcrum. Means again definition of fulcrum is same. The point at which lever is hinged, that point is known as fulcrum. Now what is the difference between this first diagram and second diagram? In both diagram, both side of band is attached or pivoted to the lever, here also and here also. But what is the difference? In first diagram, one side of the band is pivoted at the location where fulcrum is lying. Means can I say in first diagram, one side of the band is pivoted at fulcrum. But in second diagram, none of the side of the band is pivoted at the location of fulcrum. So if one side of the band is pivoted at the location of fulcrum, then that band brake is known as simple band brake. If none of the side of band is pivoted at the location of fulcrum, like in this case, left side is pivoted at this location, it is not fulcrum. Right side is pivoted at this location, it is also not a fulcrum. Means none of the side of the band is pivoted at the fulcrum, then that brake is known as differential band brake. So first we'll discuss the analysis of simple band brake. Then we'll do the analysis of differential band brake. I think you understood what is simple band brake, what is differential band brake. Okay. Now, it is one of the diagram of simple band brake. Okay. I will do the analysis of this simple band brake in detailed manner little later. But here what I want to explain, in this is drum. Over this drum, this band is wrapped. Okay. Now this band, you can see this after this point, this band is not making contact with drum, and here after this point, this band is not making contact with this drum. Means this portion of the band is making contact with the drum, and this portion of the band is making angle of theta. This angle theta is known as angle of rap or angle of contact. I think this terminology you already know. Angle of rap or angle of contact. These terminologies are important. Okay, this will, okay. Now, this is the radius of drum. These are different things. That thing will come later. But here you can see, here what I am trying to explain, how this band break acts or works. Okay. Here I am not explaining how simple band break is works. Here I am only explaining how band break works. In band break, this is lever, it is fulcrum O. We will apply braking effort P. We will apply braking effort P such that it will ensure that this brake is in tension. Sorry, this band is in tension. Because if we are using any band, any rope for any purpose, we need to ensure that band or rope is in tension, because we cannot use band or rope in compression. Okay, because if you try to compress the band, it will get fooled. Okay, so the direction of braking effort P should be such that this band should be in tension. Like in this case, you can see this side of band is pivoted as a fulcrum. Due to effort P, this point will try to move in downward direction, and if it is trying to move in downward direction, this band will be in tension because it is trying to elongate the band. Okay, now if this band is in tension, what it will do, it will create a pressure between band and drum. Why? Because when this band is in tension, it will try to push drum in this direction, but since drum is hinged at this location, drum cannot be in this direction. So due to this pressure or due to this force which is trying to push this drum in downward direction, but drum will not go in downward direction, so pressure will create in the drum. Pressure will create in the drum. And due to this pressure, normal force will come. Due to normal force, friction force will come. Due to friction force, friction torque will come. Means we will get braking action in the drum. So it is general working principle of this band brake. Okay. Means in band brake, what we need to ensure? We need to apply this braking effort such that it is ensuring this band is in tension. And how we can find the direction of that braking effort which will ensure this band is in tension, that I will explain later. But here this is the general working principle of band brake. Now we will okay, this is general band. This is the one of the diagram of band or images of band which we use generally in band brake. Here in band the portion of the band which is making contact with drum, in that portion we will attach this friction lining, because to get more braking torque we want high friction. For that we need to ensure high coefficient of friction. For that we need to attach a friction lining in the band. Friction lining is nothing but it is the part of band. Okay. Now, before starting the analysis of simple band brake or differential band brake, first we need to understand this band is in tension. It is clear. But if there is friction between drum and band, or definitely there is friction between drum and band, because we want high friction here. In that case, the tension of both sides of the band cannot be same. This thing you already studied in engineering mechanics also. If any band or any rope is wrapped over a pulley, and both sides of the band or rope is in tension, if there is no friction between band and that band or rope and that wheel or pulley, then the tension of both sides will be same. But if there is friction between band and pulley or rope and pulley, then tension of both sides cannot be same. And the side whose tension is more, that side is known as tight side. The side whose tension is less, that side is known as slack side. Okay, I will denote tension in the tight side as T1. It is my notation. And tension of the slack side as T2. Means whenever in this diagram I am writing T1 is my notation, it is the tension of tight side. I am writing T2, it is the tension of slack side. And since T1 is tension of tight side, definitely T1 will be more than T2. Now, but here important thing, how you will identify which side of the band is tight side and which side of the band is slack side. Means which side is side of tension T1, which side is side of tension T2. For that, you need to draw the combined FBD of this drum and band. From this FBD, you can find which side is tight side, which side is slack side. For that, suppose here drum is rotating clockwise and here drum is rotating anti-clockwise. Now, first in both sides of this band, draw the arrow of tension. Right now, don't conclude which side is tight side, which side is slack side. Just draw the arrow of tension. Now here in this point, if I want to apply a force which is trying to elongate this band, means which is the direction of tension for this band. For that we need to apply a tension like this. Okay. Similarly, here if we want to apply a force which is trying to elongate this band, we need to apply a tension like this. So this is the direction of tension on both sides of band. Now which side will be tight side and which side will be slack side? To find the tight side and slack side, method is written here. First read this line, then I will explain this. Okay. The side of the band which is opposite to the direction of rotation of drum will be tight side, and other side will be slack side in the combined ability of drum and band. In the combined ability of drum and band, side of the band whose direction of tension is opposite to the direction of rotation of drum, that side will be tight side, and other side will be slack side. Other side means the side whose direction of tension is same as the direction of rotation of velocity of drum, that side will be slack side. Okay. I will explain this written line here in this example. Suppose I want to find whether this side is tight side or slack side. For that, see, the direction of arrow of this tension is in the direction of velocity of drum or is in the opposite direction of velocity of drum. So this side, in this side of band, is making contact with drum at this location. Now find the direction of velocity of this point. For clockwise rotation of drum, direction of velocity of this point is this. So the direction of arrow of this side tension is same as the direction of velocity, means this side is slack side. Means if direction of tension and velocity is same, slack side. If direction of tension and velocity are opposite, then that is side is tight side. So right now this side is slack side, means tension will be T2. And if it is slack side, means definitely other side will be tight side, means this will be tight side. And you can check also. Suppose I am checking this side first, and if it is tight side, it will be slack side. So suppose I am checking this side first. So for that, this is the direction of tension. Now this side of band is attached with drum at this location. Now see the direction of velocity of this point. Drum is rotating clockwise. So direction of velocity at this location will be this. So this side, the direction of tension and direction of velocity is opposite. And if it is opposite, it will be tight side. Means this is tight side. And if it is tight side, it will be slack side. Same thing is written here. Side of band which is opposite to the direction of, whose tension is opposite to the direction of drum rotation will be tight side. Here we should write side of the band whose tension is opposite to the direction of drum rotation will be tight side, and other side will be slack side. In the ability of drum and band, you have to do this analysis in this diagram. Ability of drum and band, not on other diagrams. Don't do this analysis in the ability of lever, do this in this ability. Like suppose drum is rotating anti-clockwise. Now which side will be tight side and which side will be slack side? So first, in both sides in this ability, draw the direction of tension. It is the direction of tension for this side, it is the direction of tension for this side. Now suppose first I am doing the analysis for this side, where I am finding this side is tight side or slack side. If it is tight side, it will be slack side. If it is slack side, it will be tight side. It is 100% sure. So first I am doing the analysis of this side. So this side band, it attached with drum at this location. So we need to find the direction of velocity of this point. Drum is rotating anti-clockwise. So direction of velocity of this point will be this. So here this side tension and velocity, both direction is opposite. And if direction is opposite, means this side is tight side. I am denoting tight side tension as T1. So it is tight side. And if it is tight side, the other side will be definitely slack side. Okay, and you can also check this also. This side band is attached with drum at this location. Now we need to find the direction of velocity of this point. Drum is rotating anti-clockwise. So direction of velocity of this point will be this. Now direction of tension and velocity is same. Since direction is same, means it is slack side. Okay, so it is the method to find the which side of the band is tight side or which side is slack side. Now we will write some important relations for band break. You need to remember this relation. Okay, and this relation is always valid for all type of band break. Okay, this theta is known as angle of contact or angle of rep, already written here. Suppose T1 is the tension in the tight side, T2 is the tension in the slack side. If it is rotating clockwise, suppose it is rotating clockwise, but relation which I will write is valid for all, whether it is clockwise or anti-clockwise. For clockwise rotation, this side will be tight side, this side will be slack side. You can apply this method and you can find which side is tight side, which side is slack side. Now suppose R is the radius of drum. R is the radius of drum. T is the thickness of band. Thickness of band. Then RE is known as effective radius, and RE is equal to R plus T by 2. Why I am writing R plus T by 2? Because if we want to find the distance of this mid layer of band from this point, it will be R plus T by 2. And why this distance is important, you will come to know little later. But this distance is RE is equal to R plus T by 2. But if in question we required RE, but thickness of band is not given, then nearly we can take RE is equal to R. Because H compared to R, thickness of band will be very, very, very less. Then we can say R plus T by 2 will be nearly equal to R. If thickness of band is given, then RE, you can calculate RE by using R plus T by 2. But if thickness is not given, we will consider RE is equal to R. Okay. Now small b is the band width of the band. Now one important relation here is, I am writing the relation which are important relation here. First relation is T1 is the tension in tight side and T2 is the tension in slack side. So one of the relation between T1 and T2 is T1 by T2 will be equal to e to the power mu theta. This relation is very, very important, and it is always valid for band break. Here T1 is the tension of tight side, T2 is the tension of slack side, e to the power mu. Mu is coefficient of friction. Mu is coefficient of friction between band and drum. It will be given in the question. And theta is angle of contact or angle of rope, but in this relation we will put value of theta in radian, because again theta is coming outside, it is not coming sine in sine or cos. So whenever theta is coming separately, always put theta in radian. Okay, so here we'll put theta in radian. So it is one of the relation between T1 tight side tension and T2 that is slack side tension. Now second important relation is relation of braking torque. Okay, the formula to calculate braking torque which is coming in this drum is T1 minus T2. T1 minus T2 means difference in tight side tension and slack side tension into RE, which RE is effective radius. And what is the expression of RE? It is R plus T by 2, where R is radius of drum, T is the thickness of the band. If thickness of band is not given, then RE will be equal to R. That is different thing. Okay. So these two relation is very, very important, and you have to remember this relation. T1 by T2 is equal to e to the power mu theta, and braking torque is equal to T1 minus T2 into R. If in question mu theta is given, we will get one relation between T1 and T2. Braking torque is given, we will get another relation between T1 and T2. Two equation 2 and none, you can find T1 T2 if braking torque is given. But you have to remember these two relation. So till now what we have discussed regarding band break, we have discussed how to find which side is tight side and slack side. Okay, after finding this tight side slack side, relation between tight side tension and slack side tension is this, relation of braking torque is this. Okay, now we will start our analysis of our first break, that is simple band break. Okay, what is simple band break? That I have already discussed. If one side of the band in simple band break is pivoted at the location of fulcrum, I will denote fulcrum with O. So if one side of the band is pivoted at fulcrum O, then that break is known as simple band break. Now here, most important point, generally examiner will give braking effort direction in the diagram of lever. But suppose examiner has not mentioned what should be the direction of braking effort, then you have to find the direction of braking effort by your own. So how we will find the direction of braking effort in simple band break, that I am explaining. First we will apply braking effort at the point in this lever which is farthest from point O, because after, by doing that, with same braking effort we will get more braking action in the drum. So we will always apply braking effort in this lever at the point whose distance from fulcrum O is farthest, which is this point. Suppose I am denoting this point as Q. Now we will apply braking effort at this location. Now it should be in upward direction or downward direction. What should be the direction of braking effort, P1 or P2? How to find? We will take the direction of braking effort such that it is ensuring this band is in tension. Means the motion of this lever should be such that it is trying to elongate the band. Because if it is trying to elongate the band, means band will be in tension. For that, how you will find? Focus on that side. Imagine this side is pivoted or the fulcrum. So whether you are trying to rotate lever in clockwise or anti-clockwise, this point will not move. Okay. means this point will not move, means it will neither try to elongate the band nor try to contract the band. But by rotating the lever, this point will move. Now the motion of this point should be such that it is trying to elongate the band. Now if we want to try to elongate the band, the motion of this point should be, suppose I am denoting this point as A. This motion of this point A should be upward or downward. Upward or downward. Definitely, if point A is coming downward, it will fold the band. Means it will not try to elongate the band. But if the motion of this point A is upward, it will try to elongate the band. Means band will be in tension. So if I want, or if we want that band should be in tension, so motion of this point A should be in upward direction. Now ensure this motion of this point A should be in upward direction. Now to ensure that this motion of point A is in upward direction, we need to rotate this lever. To ensure that motion of this point A is in upward direction, we need to rotate the lever about fulcrum O in anti-clock direction. Because by rotating this lever in anti-clockwise direction, the motion of point A will be upward and it will try to elongate the band, means band will be in tension. So ultimately conclusion is, the direction of braking effort should be such that it is trying to rotate the lever about fulcrum in anti-clockwise direction. Now to rotate the lever about fulcrum in anti-clockwise direction, what effort we require to apply, whether P1 or P2? What effort we require to apply, P1 or P2? To rotate this lever in anti-clock direction, the direction of effort should be P1, because it will try to rotate the lever in anti-clock direction, and if it is trying to rotate the lever in anti-clock direction, it will try to move point in upward direction and it will try to elongate the band, means the band will be in tension. So to ensure this band is in tension, the direction of braking effort will be P1, means this will be the direction of braking effort. Okay, this will be the direction of braking effort. Again, you need not to remember this direction, you need to remember this discussion. Okay, and by this discussion you can easily find the direction of braking effort. For this case it will be in upward direction. Now if you understood, it will not depend upon whether drum is rotating clockwise or anti-clockwise. The direction of braking effort will be this, because this direction effort is ensuring this band is in tension. Now we will do the analysis of this simple band brake, first for clockwise rotation of drum, then for anti-clockwise. But whether drum is rotating clockwise, anti-clockwise, whether this band is simple band brake is simple band brake or differential band brake, these relations are always valid. I will not write this relation again. Always T1 by T2 will be equal to V to the power mu theta. Always braking torque will be T1 minus T2 into Re, and Re is this. If T is not given, take Re equal to R. Okay. Now we'll do the analysis of this simple band brake for clockwise rotation of drum. Okay, I have already made the direction of braking effort. To ensure this band is in tension, we need to apply in braking effort in this direction, and I am denoting this braking effort as P. Now to do the analysis of this band brake, we need to draw the FBD of lever and band plus drum. I am saying band plus drum. For that, what you need to do, cut this band from both sides like this. I have cut it here. Okay. Now in this FBD, first draw the FBD of this portion, means drum plus band. After that, draw the FBD of lever. Okay. First do this thing. So first we will draw the FBD of drum, and right now we are discussing for clockwise rotation of drum. So drum is rotating clockwise. So first find that which side will be tension, or tight side, or which side of the slack side. For that, first draw in this point. At this point we have cutted the band. So at this point internal force will come, or here internal force will be such that it is ensuring that band is in tension, because we already know band will be in tension. Now at this location draw a arrow which is tension for this band. And if we want to draw a arrow which is tension for this band, means we want to draw a arrow here like this. It is trying to elongate this band. For that we need to draw arrow like this. Similarly, to draw the arrow here like this, which is trying to elongate this band, we need to draw arrow like this. So it is the direction of tension. Now it is tight side or slack side, that is a different thing. We will find that. Now the tension which is coming at this location, same equal and opposite tension will come here. Again you can see this arrow is tension for this band. Okay. So if here tension is coming 500 Newton, here also tension will come in 500 Newton. Automatically arrow will be equal and opposite. Okay. Similarly, whatever tension is coming here, same equal and opposite tension will come here, because we already know whenever we are drawing any FBD, if we have cutted this band from this location, whatever internal force will come here, just equal and opposite internal force will come here. That thing you have already studied in engineering mechanics. Now to do the analysis of this brake, first we need to find which side is tight side and which side is slack side. And to find which side is tight side or slack side, we need to focus in this FBD. We need to focus in this FBD, means FBD of drum and bend. I am highlighting this portion. To find which side is tense side and slack side, we need to focus in this FBD. Now which will be tight side and slack side? Suppose first I am doing analysis for this side, whether it is tight side or slack side. Drum is rotating clockwise. So how I will do? This side band is attached with drum at this location. So first find the direction of velocity of this point. Since drum is rotating clockwise, direction of velocity of this point will be this. So here you can see direction of velocity and tension is opposite. And since direction of velocity and tension is opposite, this side will be tight side, and I am denoting tight side as tension as T1. And since it is tight side, it will be slack side. I am denoting slack side tension is T2. Now here tension is coming T1, just equal and opposite tension will come here. Here tension is T2, just equal and opposite tension will come here. So this is the FBD of lever. Okay, and in FBD of lever, this point is fulcrum O. After drawing this FBD, always take in the FBD of lever, net moment about fulcrum O equal to 0. In the FBD of lever, always take net moment about fulcrum O equal to 0. If you will do this, it will come. First, a moment of effort P, it is P, its perpendicular distance from O is L. Now direction of movement of this effort P about O is anti-clockwise. Suppose I am considering clockwise as positive and anti-clockwise as negative, so it will be minus. Now direction of movement, moment of force T1, it is T1, its perpendicular distance from O is A. Now direction of movement due to this T1 about O is clockwise. I am considering clockwise direction as positive. Now T2, since T2 is passing through O, so its movement about O will be 0. And since its movement about O is 0, we need not to write this. Again, we will not write the moment of reaction of this hinge point. Why? Because we are taking moment about hinge point or fulcrum, and reaction will also come at this location also, location O. So the perpendicular distance of reactions at O will be 0 from O, means the moment of reaction which is coming at location O will be 0 about O. That's why we are taking net moment about fulcrum O, because moment of reaction of hinge point about O will be 0. So it is net moment about fulcrum O. From this relation we will get the relation of braking effort P. It will come T1A upon L. You need not to remember this relation. From this FBD you can easily find this relation. Okay, only you have to remember two relations. One is T1 by T2 is equal to e to the power mu theta, and braking torque is equal to T1 by minus T2 into Ra. Now if examiner has given braking torque, so he will ask what is the braking effort. So from braking torque or torque we will get one relation between T1 T2. One relation between T1 T2 we already know, T1 by T2 equal to e to the power mu theta. From those two relations we can find the T1 and T2. After finding T1 and T2 from this relation you need not to remember, from this FBD you can easily find. You can find braking effort. Similarly, sometimes examiner will give braking effort and ask about braking torque. So if examiner is giving braking effort, from this relation we can find the relation between T1 T2. One relation between T1 T2 we already know, T1 by T2 equal to e to the power mu theta. From those two relations we can find T1 T2, and if you have found T1 T2 you can find braking torque by using relation T1 minus T2 into Ra. Very simple. Now we will try to make some conclusion. If I will ask whether this simple band brake for clockwise rotation of drum is self-energizing or not, for that see whether here any term is coming which is trying to reduce braking effort. No. Since here no term is coming which is trying to reduce braking effort, so can I say simple band brake for clockwise rotation of drum is not a self-energizing brake? Is not a self-energizing brake, because no part is coming which is trying to reduce the braking effort. And since it is not a self-energizing brake, can I say it will never go in self-locking condition, because P will never become 0 or negative, it will always be positive. So this brake will never be in, it can never be in self-locking condition. Okay, so it is simple band brake for clockwise rotation. Now we will do the analysis of simple band brake for anti-clockwise rotation of drum. So here drum is rotating anti-clockwise. Whether drum is rotating clockwise, anti-clockwise, it will not change the direction of braking effort, because this direction of braking effort is ensuring this band is in tension. Okay. Now we'll draw the FBD of drum and lever. FBD of drum plus band and lever. For that, again we'll cut this band from both sides like this. Okay. Now if we'll draw the FBD, first draw this FBD, then draw this FBD. Now here draw a arrow which is trying to elongate this band. For that we need to apply arrow like this. It is the tension of this side. Similarly, draw arrow here which is trying to elongate this band. For that we need to draw arrow like this. Drum is rotating anti-clockwise. Whatever tension is coming this side, same equal and opposite tension will come here. Whatever tension coming in this side, same equal and opposite internal force will come here. Now first we need to find which side is tight side, that is side of tension T1, which side is slack side, that is side of tension T2. For that we will use this FBD. Now in this FBD, suppose first I am doing the analysis of this side, whether it is tight side or slack side. For that, this side of the band is making contact with drum at this location. So we need to find the direction of velocity of this point. Drum is rotating anti-clockwise. So direction of velocity of this point will be this. So here you can see the direction of tension and velocity is same. And if direction of tension and velocity is same in this FBD, means that side will be slack side. So this side is slack side. And I am denoting tension of slack side as T2. So it is the slack side, means here tension will be T2. Since it is slack side, other side, that is this side will be tight side, means here tension will be T1. Now whatever tension is coming here, here T2 is coming, just equal and opposite tension will come here. Similarly, whatever tension is coming here, just equal and opposite tension will come here. Now, in this FBD, we'll take in the FBD of lever, in FBD of lever, take net moment about fulcrum O equal to 0. It will come. First moment of effort P, it is P, its perpendicular distance from O is L. Now direction of movement of effort P about O is anti-clockwise. Suppose I am taking clockwise as positive, anti-clockwise is negative. So since it is anti-clockwise, we will use minus sign. Now movement of T2 is perpendicular distance from, take perpendicular distance. Since it is vertical, we need to take horizontal distance. So its horizontal distance from O is A. So its movement will be T2 into A. Direction of movement of T2 about O is clockwise. I am taking clockwise direction as plus. Now moment of T1, since T1 is passing through O, its movement will be 0. So it is net movement about fulcrum O. From this relation, you will find the relation of P. It will come T2A upon L. Okay, so it is the braking effort relation. Again, you need not to remember this relation. Okay, but from this relation, can I say whether this brake is self-energizing or not? Yes, sir, you can conclude. This brake is not self-energizing because here no part is coming which is trying to reduce the braking effort. So can I say simple band brake for anti-clockwise rotation also is not a self-energizing brake? And since it is not a self-energizing brake, can I say it can never be in self-locking condition, because P will always be greater than 0. So here we can make one conclusion. If you want, you can remember this conclusion. For simple band brake, whether drum is rotating clockwise, because for clockwise rotation of drum, we have made conclusion it is not a self-energizing brake and it can never be in self-locking condition. For anti-clockwise rotation of brake, also same conclusion we have made about self-energizing and self-locking, that this brake is not self-energizing and it can never be in self-locking condition. So can I conclude, in simple band brake, whether it is rotating clockwise or whether it is rotating anti-clockwise, brake will never be self-energizing brake. Simple band brake will never be self-energizing brake. Simple band brake is not a self-energizing brake, whether drum is rotating clockwise or anti-clockwise. Okay, and if it is never, it is not a self-energizing brake, it can never be in self-locking condition. So we can also say simple band brake can never be in self-locking condition. If you want, you can remember this conclusion regarding simple band brake. Suppose, but for simple band brake, examiner is asking which case is more effective, means, but you need not to remember, only understand. For clockwise rotation of drum, simple band brake is more effective if diagram is this, or for anti-clockwise rotation. So see, out of these two case, in for same T1 T2 value, same T1 T2 value means braking torque is same. So for same braking torque or for same T1 T2 value, in which case braking effort P value is coming less. So in case 1, braking effort P is T1 A upon L, it is coming in terms of T1. In case 2, braking effort P is coming T2 A upon L, it is coming in terms of T2. T1 is more than T2. So can I say in first case braking effort will be more for same value of T1 T2. In second case braking effort will be less. And since in second case braking effort is less, but braking torque is same both in the both case, because I have taken the same value of T1 and T2. And out of T1 and T2, a value of T1 will be more, T2 will be less. And in case 1, P is coming in terms of T1. In second case, P is coming in terms of T2. So definitely for case 1, P will be more. For case 2, P will be less for same value of T1 and T2 of braking torque. And since for second case braking torque is less, to get same braking action. So can I say out of this case 1 and case 2 is more effective? Can I say out of this case 1 and case 2, the diagram which I used here, case 2 is more effective than, in case 2 drum was rotating anti-clockwise, then case 1, in case 1 drum was rotating clockwise for this diagram. Why? Because for same braking torque in case 2 braking effort is less as compared to case 1. So time if question is coming for a simple band brake, this conclusion you can directly remember. Brake will not be self-energizing brake and it can never go in self-locking condition. Now if examiner asking for which rotation of drum brake is more effective, so find the relation of braking effort for clockwise rotation also, find the relation of braking effort for anti-clockwise rotation also. After that, see for which rotation of drum braking effort value is coming less for same braking torque, and that case will be more effective. Like in this diagram, case 2, that is anti-clockwise rotation of drum case, is more effective than case 1, that is clockwise rotation of drum, because for case 2 P is coming less. Okay, so this is the analysis of simple band brake. It is completed. Okay, now important relation for simple band brake, this relation are always value T1 by T2 equal to e to the power mu theta. Braking torque is T1 minus T2 into Re. Along with that, by using this FBDs we can find the relation between P, T1 and T2. You need not to remember this, easily you can find this. Now I am solving some questions. These are very easy questions. This is first question. What this question is saying, a force F is applied to the brake drum of 0.5 meter diameter. Diameter is 0.5 meter, so radius will be half of diameter, that is 0.25 meter. In a band brake system shown in figure, where the wrapping angle is, that is angle of rope theta, is given 180 degree. Convert this in radian. In radian it will be pi radian. Yes sir. Coefficient of friction between the drum and band, that is mu, is given 0.25. Since mu and theta is given, we can find one relation between T1 and T2. It will be equal to T1 by T2 will be equal to e to the power mu theta. Now braking torque examiner is asking. This question is very simple. Why? Because here directly this value is given. Again what we will do, we will cut this band. We will cut this band from both sides. So if we will cut from this side, diagram will be like this. If we will cut from this side, diagram will be like this. So we have cutted this band from both sides. Now first draw the direction of tension. Here we'll take arrow such that at this point, which is trying to elongate this band. For that we need to take arrow like this, and equal and opposite tensile will come here. Again here draw tension like this. It is trying to elongate this, means it will be like this. Equal and opposite tension will come here. Now first find which side will be tight side and which side will be slack side. To find which side is tight side or which side is slack side, use this FBD. Okay, now in this FBD, which side is tight side or slack side? So suppose first I am doing the analysis for this side, whether it is tight side or slack side. So in this side, band is attached with drum at this location. So we will find the direction of velocity of this point. Drum is rotating anti-clockwise. So at this point, direction of velocity will be this. Now the arrow of this side tension is same as direction of velocity. Means can I say in this diagram this side will be slack side? So this side is slack side, or slack side tension I am denoting as T2. And since this is slack side, it will be tight side, that is tension of tight side, that is T1. Now equal and opposite tension will come here, means it will be T2. Equal and opposite tension will come here, it will be T1. Now what we will do? From this FBD we can find the value of T1. How? In this FBD it will be in equilibrium, means net force in x direction will be 0. And in this FBD if you will apply net force in x direction equal to 0, that is horizontal direction, how will find this relation? Suppose I am adding this side force and subtracting this side force. So in this FBD 400 is coming here, I am adding this. T1 is coming here, I am subtracting this. It will be equal to 0. So from this equation we will get the value of T1, which is coming 400 Newton. Now since mu and theta is given, we can find the relation between T1 T2. From that relation, since we have calculated T1, we can find T2. How? T1 by T2 will be equal to e to the power mu theta. Now T1 by T2 will be equal to e to the power mu. Mu is coefficient of friction, which is 0.25, and theta is angle of contact, which is pi. So from this relation we get the relation between T1 and T2. And since T1 is already we have calculated, we can find T2. T2 will be equal to T1 upon e to the power 0.25 pi. Yes sir. T1 is 400 divided by e to the power 0.25 pi. So from this equation we can find the value of T2. And how much it is coming? 400 divided by e to the power 0.25 pi. It is coming 182.375 Newton. Since we have calculated the value of T1 and T2 both, we can find braking torque. And formula to calculate braking torque is T1 minus T2 into Re. T1 is 400 minus T2 is 182.375 into Re. Formula to calculate Re is R plus T by 2. But since thickness of band is not given, we will neglect this term. So Re will be equal to R, which is 0.25 meter. So here Re is equal to R, which is 0.25. So from this equation we can find braking torque, and how much it is coming? It is coming 54.406, and since we have used SI unit, so braking torque will be in Newton meter. So in Newton meter, for this question, value of braking torque is 54.406. So examiner has a braking torque in Newton meter, which is coming 54.4. Which option is correct? Option B. So for this question, correct answer is option B. Okay. We will solve one more question. In this question, see this angle carefully, it is 60 degree. Now, here braking effort P is given. Angle of rep, that is theta, is 240 degree. Convert this into radian. If we will convert this into radian, it will be d by 180 equal to theta by pi. So it will be 240 by 180 into pi radian. How to convert degree into radian, that you should know. It is your homework if you don't know. Find how to convert degree into radian. It is coming 240 divided by 180 into pi. It is coming 4.1888 radian. This is angle of contact. Coefficient of friction, that is mu, is given 0.3. Since mu and theta is given, we can find one relation between T1 and T2. Now here radius of drum is given 150 mm, means 0.15 meter in SI unit. Braking torque examiner is asking. So what is the formula to calculate braking torque? T1 minus T2 into Re. So to find braking torque, first we need to find T1 and T2. Now T1, T2, two unknown. So one relation we can find between T1 and T2 by using T1 by T2 equal to e to the power mu theta. It is one relation. Now another relation, since braking effort is given, so from the FBD of lever we can find the relation between P, T1 and T2. So again two equation, two unknown, we can find T1 and T2, and after finding T1 and T2 we can find braking torque. So first, by using this FBDs of lever, first we need to find the relation between P, T1 and T2. So to draw the FBD of this, we need to cut band from both sides, from this side and this side. If we'll cut band from this side, it will look like this. Now draw a arrow at this location like this. It is trying to elongate the band, and to elongate the band we need to draw arrow like this. So arrow of tension for this side will be this. Again draw at this location arrow like this. It is trying to elongate the band. For that we need to like apply arrow like this. Now whatever tension is coming here, same equal and opposite tension will come here. Whatever tension is coming here, same equal and opposite tension will come here. Now we need to find which side of this band will be tight side and which side of this band will be slack side. For that, to find which side is tight side or slack side, we use this FBD. Now in this FBD, suppose first I am doing the analysis for this side. I am finding whether this side is tight side or slack side. How to find? Drum is rotating clockwise. So how to find? See, this side of band is attached with drum at this location. So see the direction of velocity at this location. Drum is rotating clockwise. So direction of velocity of this point will be this. Now the direction of velocity and tension is opposite, and since direction is opposite, this side will be tight side, and I am denoting tight side tension as T1. So it is the side of tension T1, and since it is tight side, it will be slack side, and tension of slack side is T2. Now whatever tension is coming here, equal and opposite tension will come here. Whatever tension is come here, equal and opposite tension will come here. Now what we will do, in the FBD of lever, it is fulcrum O, will take in the FBD of lever, will take net moment about fulcrum O equal to 0. Now I am taking net moment about fulcrum O. Now to find the moment of this tension T1 about O, we need to find perpendicular distance of this T1 from O. Now T1 is inclined and we know horizontal distance. So what you can do, one method is find the perpendicular distance of this T1 up from O, or you can also, what you can do, you can resolve this T1 in vertical and horizontal direction and take the moment of vertical component about O and horizontal component about O. And if you have taken that moment of horizontal component and vertical component about O, means you have taken the moment of T1 about O. So the second approach is more easier. Resolve this T1 in vertical and horizontal direction, because we already know horizontal distance and vertical distance. Vertical distance of this point from O is 0. Horizontal distance of this point from O is 50 mm. That we already know. So I am resolving this tension T1 in vertical and horizontal direction. The angle of this T1 from horizontal is 60. So its vertical component will be like this and horizontal component will be like this. Now since this angle is 60, so this angle is 60, it is angle from horizontal. So with horizontal component cos 60 will come, with vertical component sin 60 will come. Means this vertical component will be T1 sin 60 and this horizontal component will be T1 cos 60. Now we can easily take the moment of this vertical component or horizontal component about O. We need not to resolve T2 because T2 is passing through O, means its moment about O will be 0. So in this FBD I am taking net moment about O. First I am taking the moment of this effort, that is 1000 Newton force. It will be, force is 1000. Now see its perpendicular distance from O. Since it is vertical, we need to see horizontal distance, and horizontal distance of this point from O is 200 plus 50, that is 250 mm. So it is 250. Now direction of movement due to effort P about O is anti-clockwise. Suppose I am taking clockwise direction as positive and anti-clockwise as negative, so we will use minus sign. Now movement of this vertical component of T1, that is T1 sin 60. So first this vertical component is T1 sin 60. Now its moment, so we need to find perpendicular component distance of this component from O. Since it's vertical, its perpendicular distance will be horizontal. So horizontal distance of this force from O is 50 mm. So perpendicular distance is 50. Now direction of movement due to this force about O is clockwise, and I am taking clockwise direction as positive. So here we will use plus sign. Now moment of this force T1 cos theta about O. You can see that T1 cos theta is horizontal. So to find its movement, we need to find the vertical distance of this force from O. And since you can easily see this force is passing through O, means vertical distance of this force from O is 0. So moment of this T1 cos theta component will be 0 about O. And since it is 0, we need not to write here this. Similarly, moment of T2 about O is 0 because T2 is also passing through O. Moment of reaction of this hinge support will be 0 about O because hinge support reaction will come at location O, means its perpendicular, their perpendicular distance from O will be 0. Means it is the total moment about fulcrum O for the FBD of lever, and we will equate this with 0. And since braking effort is already given, we can easily find from this value of T1. It will come, T1 will come, this minus will come this side, it will become plus 1000 into T50 divide by 50 sin 60. From this equation we'll get the value of T1. How much it is coming? 1000 into 250 divide by 50 divide by sin 60. It is coming 5773.502 Newton. It is the value of T1. Now, since mu and theta is given, we can find the relation between T1 and T2. Since we have already calculated T1, from that relation we can calculate T2. How? How? What is the relation between T1 and T2? T1 by T2 is equal to e to the power mu theta. Yes, sir. T1 by T2 is equal to e to the power mu. Mu is coefficient of friction. And for this question, coefficient of friction mu is 0.3 into theta. Theta is angle of contact. For this question, angle of contact or angle of wave is 4.1888 radian. 4.1888 radian. So from this relation we can find the relation between T1 and T2, and it is coming e to the power mu theta, that is e to the power 0.3 into 4.1888. It is coming 3.5136. And since we have calculated the value of T1, which is 5773.502, if you will put this value here, we can find the value of T2. So from this equation, if you will find the value of T2, it will come T1 upon, and T1 is 5773.502 divide by 3.5136. So by solving this, we will get the value of T2. And how much it is coming? It is coming 5773.502. From there, you will calculate the value of T2. It will come 1643.189 Newton. And after calculating value of T1 and T2, we can calculate braking torque. What is the formula to calculate braking torque? It is T1 minus T2 into Re. Here T1 is 5773.502, 5773.502 minus T2, and T2 is 1643.189, 1643.189 into Re, and Re is since thickness of band is not given, we will take Re equal to R, which is 0.15 meter. So for this question, Re is equal to R, which is 0.15. So we will get the value of braking torque, and it is coming 5773.502 minus 1643.189 into 0.15. It is coming 619.54 Newton meter. Okay. So braking torque for this question is 619.54 Newton meter. Okay. Examiner is asking in kilonewton meter. So braking torque in Newton meter is 619.54. So in kilonewton meter it will be 0.61954 kilonewton meter. So see the unit carefully. In which unit examiner is asking? He is asking in kilonewton meter. So it will be 0.61954 kilonewton meter. 0.61954 kilonewton meter. Okay. So this is the we have completed the analysis of band brake, and in that analysis we have completed analysis of simple band brake. Now we will start the analysis of differential band brake. Okay. So now we will discuss the analysis of differential band brake. So now we will discuss differential band brake. First, in differential band brake, we will discuss how to find the direction of braking effort. How to find the direction of braking effort. What is differential band brake? If it is the lever, this lever is hinged at this location, so it is the location of fulcrum O. If in band brake, none of the side of band is pivoted at the location of fulcrum, means that band brake is known as differential band brake. Here you can say this left side band is pivoted at this location. Suppose I am denoting this location as a right side band is pivoted at this location. Suppose I am denoting this location as B, and none of the side is pivoted at the location of fulcrum, means it is differential band break. Now how to find the direction of braking effort, means what should be the direction of braking effort in this case? In this case, first we will apply the braking effort at this location, because this point is farthest from point O. Suppose I am denoting this point as Q. Now at this location, what should be the direction of braking effort, whether it should be upward or downward? Either it will be upward or downward, but what should be the direction, whether it should be upward or downward? For that we need to see whether this distance, means distance of point B from fulcrum, is more, or this distance, that is distance of point A from fulcrum, is more. If it is numerical, by looking in the value you can see. But here, if it is not a numerical, examiner will mention whether A is more or B is more. Right here I have mentioned that B is greater than more. B is greater than more means this distance is more and this distance is less. Now how to find the direction of braking effort? For that, first focus on that side of band whose distance from fulcrum is more. Right now, which side band distance is from fulcrum is more? Right side or left side? Right side band distance is more from fulcrum as compared to left side band, because B is more than A. Now since this distance is more, so focus in this side of band. Now you will take the direction of braking effort such that, due to that, the movement of point B should be such, it should try to elongate the band. Now if we want to try to elongate the band, the motion of point B, why I am focusing on point B? Because its distance from fulcrum is more as compared to this point. Okay, that's why I am focusing on point B. Now to ensure this band is in tension, the motion of point B should be such that it is trying to elongate the band. Now to elongate the band, the motion of point B should be in this direction, because it will try to elongate the band. Now to ensure that motion of point B in this direction, lever should rotate about O in anti-clockwise direction, because this direction movement about O is anti-clockwise. So to ensure this point B is moving in this direction, the movement of this lever about O, means this lever should rotate about O in anti-clockwise direction. So the direction of braking effort should be such that it should try to rotate the lever about fulcrum in anti-clockwise direction. Now to rotate the lever about O in anti-clockwise direction, we need to apply braking effort in this direction. Why? Because this direction is trying to rotate the lever about O in anti-clockwise direction, and since it is trying to rotate lever in anti-clockwise direction, it will try to move this point B in upward direction, means it will try to elongate that side of band whose distance is more from point O. It is try to elongate that side of band whose distance is more from point O, means ultimately band will be in tension. So in this question, this should be the direction of braking effort. So here correct direction of braking effort is direction P1, that is this direction. Direction P1, that is this direction. Suppose in this same question, if A is more, if right now B is more, but if A is more, so you will focus in this point, means motion of this point should be such that it is try to elongate the band. For that, point A should go in upward direction. Now to move point A in upward direction, we need to rotate lever about O in clockwise direction. To rotate lever in clockwise direction, we need to apply in braking effort in this direction. So direction of braking effort will depend whether this distance is more or this distance is more. Right now this distance is more, so we have focused in this point B. The motion of point B such that it should try to elongate the band. For that, it should move in upward direction. For that, lever should rotate anti-clockwise. For that, we need to apply braking effort in this direction. Okay, so this is the way to find the direction of braking effort. Okay, it will not depend whether drum is rotating clockwise or anti-clockwise. It will not depend upon the direction of rotation of drum. Like this is one question, it is MSQ, means more than one option can be correct. Here examiner is asking which one or more of the following options are correct. For clockwise rotation of drum, option is correct braking effort direction is P1. For anti-clockwise, correct braking effort direction is P2. For clockwise, correct braking effort direction is, here it is typing error, it is P2. For anti-clockwise, correct braking effort direction is P1, it is P1, it is typing error. Okay, so we have to find for clockwise or anti-clockwise which direction of braking effort is correct. But direction of braking effort will not depend upon rotation of drum. Means for both rotation, direction of braking effort will be same whether it is P1 or P2. But how to find that direction? For that, suppose this fulcrum I am denoting as A. This side band is pivoted here. I am denoting this point as A. This side band is pivoted here. I am denoting this point as B. Now first see which side of band is distance of which side of band is more from fulcrum O. So this distance is 100 and this distance is 50. Means the distance of this side band, that is point A, is more for fulcrum. So here we will focus on point A while concluding what should be the direction of braking effort to ensure band is in tension. So we will focus in point A. Now motion of point A should be such that it is trying to elongate the band. Now to elongate the point A should move in this direction. Yes sir. Now to move point A in this direction, we need to rotate this point A about fulcrum in clockwise direction. Means ultimately we need to rotate this lever in clockwise direction. So if we want to ensure that this band is in tension, this lever should rotate clockwise. Now to rotate lever in clockwise direction, in which direction we need to apply this braking effort? If we will apply braking effort in this direction, then moment of the force of this direction about O is clockwise, means drum lever will rotate clockwise. If I apply braking effort in this direction, due to this force, moment about fulcrum will be anti-clockwise. And right now to ensure this band is in tension, we want lever should try to rotate in clockwise direction. For that we need to apply braking effort in this direction, because this force will try to rotate this lever in clockwise direction. Means here correct direction of braking effort is direction P2. Okay. So for clockwise rotation of drum, correct braking effort direction is P1. Is it incorrect? Because correct direction is P2. For anti-clockwise, correct braking effort direction is P2. B is correct. For clockwise, correct braking effort direction is P2, because it will not depend upon the rotation of drum, whether it is clockwise or anti-clockwise. To ensure that band is in tension, we need to apply effort in P2 direction. Okay. For anti-clockwise, correct direction is P1. Again, it is incorrect. So correct options for this question are option B and option C. Okay. So in this way we can find the braking effort direction. Now we will do the analysis of band brake. We will do the analysis of differential band brake. Okay. So first we are doing the analysis of differential band brake for clockwise rotation of drum. But we are doing this analysis when B is greater than A. So whatever conclusion is coming here, don't memorize this conclusion, only understand the concept. Okay. Because sometimes question can come when A is greater than B. Okay. Right now since B is greater than A, in that case correct braking effort direction will be this. Why sir? B is greater means this point distance from fulcrum is more. So to find the correct direction of braking effort, the motion of point B should be such that it is trying to elongate the band. For that point B should move in this direction. For that point B should move in this direction. For that lever should rotate about fulcrum in anti-clockwise direction. To rotate lever anti-clockwise direction, we need to apply braking effort in this direction, because this direction is trying to rotate lever in anti-clockwise direction. So this direction is correct. Okay, if this effort direction is directly given in the question, then we can conclude by looking this direction whether B is greater more or A is more. Examiner need not to give B is greater than A or A is greater than B, because by looking this direction you can see this direction is trying to rotate the lever in anti-clockwise direction. Due to this, B will go upward and this point will go downward. B is going upward means it is trying to elongate the band. Since this motion of B is trying to elongate the band, so to ensure this band is in tension, the distance of this point B should be more from O as compared to distance of this point. Means for that small b should be greater than smaller. But right now it is mentioned already in the question. Now we will do the analysis. But during analysis, again this two relation is common. Again T1 by T2 will be equal to e to the power mu theta. Braking torque will be T1 by T2. Braking torque relation will be T1 minus T2 into Ra. Ra is R plus T by 2. R is radius of drum, T is thickness of wind. If T is not given, we will consider take Ra equal to R. Okay, this relation are same for all band brake. Here analysis means by using the FBD of lever, we need to find the relation between P and T1 and T2. And how we will find? For that, first we will draw FBD. To draw the FBD, first we will cut band this from both sides. If we will cut the band from both sides, it will look like this. Now, at this location, apply a arrow which is trying to elongate the band because band is tension. For that, we need to take arrow in this direction. Again, in this direction, apply a arrow which is trying to elongate this band. Okay, whatever tension is coming here, equal and opposite tension will come here. Whatever tension is coming here, equal and opposite tension will come here. Now to find which side is tight side or which side is slack side, we will refer this FBD. Now in this FBD, Suppose I am first doing analysis for this side. I am finding this side is tight side or slack side. Right now drum is rotating clockwise. It is mentioned in the question. Now suppose I am focusing on this side tension. This side band is attached with drum at this location. So find the direction of velocity at this point. Direction of velocity at this point, since drum is rotating clockwise, so direction of velocity of this point will be this. Now see that this side tension is opposite to the velocity, and since this side tension is opposite to the velocity, this side will be tight side, means this side will be tight side of tension T1, and since it is tight side, it will be slack side, so it is the side of tension T2. Whatever tension is coming here, equal and opposite tension will come here. Whatever tension is coming here, equal and opposite tension will come here. After that, what we will do, in the body of lever, it is fulcrum O. We'll take net moment about fulcrum O equal to 0. Okay, so what will be this equation? Now, first moment of effort P about O. It will be P, its perpendicular distance from O is L. Now, direction of movement is anti-clockwise. Suppose I am taking clockwise as positive, anti-clockwise as negative. Now, it is T1, its perpendicular distance from O is B. So its movement will be T1 into B. Now direction of movement of T1 about O is clockwise. I am taking clockwise as positive. Now moment of tension T2, it is T2. Its perpendicular distance from O is A. Now direction of movement about O is anti-clockwise. I am taking anti-clockwise direction as positive. Now this is equal to 0. From this equation, if you will calculate value of P, it will be, it is minus. So this minus will come this side, it will become plus. Here I have made one mistake. Since direction of movement of T2 about O is anti-clockwise, and I am taking anti-clockwise direction as negative, so it will be minus. Now since it is minus, we will shift this minus here, so it will become plus. So ultimately this relation will come, you can check calculation, T1B minus T2A divided by L. Okay, and ultimately tension T1 and T2, it is the relation between P, T1 and T2. Okay, ultimately T1 and T2 is inducing due to friction, and is in this relation sub part is coming which is trying to reduce the braking effort. Yes, here you can see T2A part is trying to reduce the braking effort, and since T2A part, because it is coming with minus, is trying to reduce the braking effort, so can I say this differential band brake for clockwise rotation of drum is self-energizing brake, because here some part, and that part is T2A part, is coming which is trying to reduce the braking effort. So I make a conclusion here that for clockwise rotation of drum, this differential band brake is self-energizing brake. Due to which part? Due to tension T2. Why? Okay. Examiner will simple ask whether it is self-energizing or not, but here I am extending this. It is self-energizing due to tension T2. Okay, and you can also conclude this is self-energizing due to tension T2 without writing this equation, just visualizing the direction of movement of effort P and tensions. When I was discussing shoe brake, I already discussed that if direction of movement of effort P about fulcrum and direction of movement of friction force about fulcrum is same, means that brake will be self-energizing, because in that case friction will try to reduce the braking effort. Similarly here, whatever the direction of movement of effort P, suppose if it is clockwise or anti-clockwise, so in that direction, if suppose the direction of movement of T2 about fulcrum is same the direction of movement of effort P about fulcrum, then T2 part will try to reduce the braking effort, and due to that part brake will be self-energizing brake. If direction of movement of tension T1 about fulcrum is same as direction of movement of effort P about fulcrum, then T1 part will try to reduce the braking effort, and then brake will be self-energizing due to T1 part. But if direction of neither T1 nor T2 about direction of movement of neither T1 nor T2 about O is same as P, as direction of movement of effort P, then that brake will not be self-energizing. So here if you will only focus on direction, so we can see about O, direction of movement of effort P about O. If you don't want to derive this equation, only you want to see whether it is self-energizing or not, due to which tension. So direction of movement of effort P about O is anti-clockwise. Now direction of movement of tension T1, it is tension T1 about O is clockwise. Now T2, direction of movement of tension T2 about O in the body of lever about O, it is anti-clockwise. So you can see the direction of movement of effort P is anti-clockwise and direction of T2 is also anti-clockwise about fulcrum. Means direction of movement of T2 is same as direction of movement of effort P about fulcrum. Means this brake will be self-energizing due to this T2 part. Okay, in this way you can calculate if you don't want to derive this equation. Okay, now since it is self-energizing, it can go in self-locking condition also, or it cannot be go in self-locking. If we want to avoid self-locking condition, so what we need to ensure? To avoid self-locking condition, P must be greater than 0. Yes, sir. Now to ensure P must be greater than 0, this above part should be greater than 0. Means can I say to ensure P is greater than 0, T1B minus T2A must be greater than 0. Yes, sir. From this you can derive T1B must be greater than T2A. From this you can conclude that T1 by T2 must be greater than A by B. Please see carefully. Okay, T1 by T2 is e to the power mu theta. So you can say e to the power mu theta must be greater than A by B. Means LHS should be more than RHS. Whenever this equation will satisfy, brake will not be in self-locking condition for clockwise rotation of drum. Okay, don't memorize this, only understand. Or if examiner is asking what will be the relation to avoid self-locking condition, derive this expression, because right now B is greater than more A. In other case A can be more than B, but in that case direction of effort will change. Okay, now here to ensure this is to avoid self-locking condition, e to the power mu theta must be greater than A by B. But here one interesting result is coming. Can I say e to the power mu theta will always be more than 1? Why? Because e to the power mu theta is ratio between T1 by T2, and T1 is more than T2, means e to the power mu theta will always be more than 1. But here in this case, since B is greater than A, so can I say in this case A by B ratio is always less than 1. Now it is always more than 1 and it is always less than 1. Suppose it is 1.1 and it is 0.9. Since it is more than 1, it is less than 1. So can I say in this case LHS will always be greater than RHS? Means in this case this equation will always satisfy. Always satisfy. Means we need not, for this case we need not to check whether it is greater than this or not. Because e to the power mu theta will always be greater than A by B. Why? Because e to the power mu theta is more than 1 and this part is less than 1. So here always LHS will be greater than RHS. Means can I say this equation will always satisfy? And since this equation will always satisfy, so can I say in this case brake will never go in self-locking condition, because this is the condition to avoid self-locking and it will always satisfy for this case. Means can I say in this case brake is self-energizing, then also this brake can never go or can never be, will be in self-locking condition. Or if you want to remember, you can remember this like this. If brake is self-energizing due to lesser tension, here brake is self-energizing due to T2. T2 is lesser tension. In that case, brake will never go in self-locking condition, because it will always satisfy that condition which we need to satisfy to ensure that brake is not going in self-locking condition. Okay, so this brake is that's why I have written it is self-energizing due to tension T2, slack side tension. And if brake is it is self-energizing, but it is self-energizing due to slack side tension, that it will never go in self-locking condition. Okay, now we will discuss second case. Same case, and B is greater than A, but for anti-clockwise rotation of drum. Means right now now drum is not rotating clockwise, it is rotating anti-clockwise. Okay, now to do the analysis of this condition, we will cut this bend from both sides and draw the FBD. Now first apply an arrow like this, which is tension for this bend, means which is trying to elongate the bend. We need to apply arrow like this, and same equal and opposite tension will come here. Again apply arrow like this, which is trying to elongate this bend. We need to apply arrow like this, and equal and opposite tension will come here. Drum is rotating anti-clockwise. Now we will find which side is tight side and which side is slack side. For this we will focus on this part. Now first suppose I am focusing on this tension, whether it is tight side tension or slack side. For that, this side bend is attached with drum at this location. So we will find the direction of velocity of this point. Since drum is rotating anti-clockwise, direction of velocity of this point will be this. Direction of velocity of this point will be this. Now direction of tension and velocity is same, means this side is slack side, means tension of this side will be T2, and since this is slack side, other side will be tight side, means this side is tight side. Now whatever tension is coming here, equal and opposite tension will come here. Whatever tension is coming here, equal and opposite tension will come here. This is fulcrum O. After drawing this FBD, in the FBD of lever, we'll take net moment about fulcrum O equal to 0. And it will be the moment of effort P about O is P, is perpendicular distance from O is L. Now direction of moment of effort P about O is anti-clockwise. Suppose I am taking clockwise is plus, anti-clockwise is minus. So since it is anti-clockwise, I am taking minus. Now moment of T2, it's T2, its perpendicular distance from O is B. Now direction of moment of T2 about O is clockwise, I am taking clockwise direction is plus. Now it's T1, its perpendicular distance from point O is A, its moment about O is anti-clockwise, and I am taking anti-clockwise direction is minus, equal to 0. From this equation, if you will find the relation of effort P, it will come, this is minus, it will come this side, it will become plus. So it will come T2B minus T1A divided by L. So again, from this equation you can see, again here some part is coming which is trying to reduce the braking effort, means again it is self-energizing brake. But due to which tension, tight side or slack side tension? It is self-energizing due to tension T1, because this part is trying to reduce the braking effort. So can I say this brake for anti-clockwise rotation of drum, don't remember this conclusion, because right now B is greater, in some other case A can be greater than B. Okay, so it might be possible, for that case it will be self-energizing due to, right now for anti-clockwise it is self-energizing due to tension, but in another case it might be possible it will become for clockwise rotation self-energizing for clockwise rotation, but due to tension T1. So don't remember the conclusion. Whatever you need to remember, I will explain separately. Like you can remember this. See the direction of moment of effort P about O, direction of moment of tension T1 about O, direction of moment of tension T2 about O. If direction of moment of tension T2 and effort P is same, then it will be self-energizing due to T2. If direction of moment of tension T1 and effort P is same, then it will be self-energizing due to T1. That I will explain here also. But from this relation also you can conclude this brake is self-energizing due to tension T1. Okay, and you can conclude this one more with one more A. For that, see the direction of movement about fulcrum O for effort P. Only see the direction. Direction of movement of effort P about O is anti-clockwise. Now see the direction of movement of tension T1 about O. It is T1. Its movement about O is also anti-clockwise. Now see the direction of movement of tension T2 about O. The direction in the FBD of lever. The direction of movement of tension T2 about O is clockwise. So from this you can see the direction of movement of tension T1 and P is same, means this brake is self-energizing due to tension T1. Same conclusion, due to tension T1. Now here if you want to avoid self-locking condition, to avoid self-locking condition, what we need to ensure? P must be greater than 0. Now to ensure P is greater than 0, we need to ensure this above part is greater than 0. This above part is T2B minus T1A. T1A must be greater than 0. To ensure this, T2B must be greater than T1A. Now to ensure this, T2 by T1 must be greater than A by B. Or you can also write equation like this. If you want to write it as T1 by T2, you need to take the reciprocal of this. But if here you are taking reciprocal, here also you will take reciprocal. But doing this, the greater sign will become less sign. If we are reversing this T2 by T1 as T1 by T2, A by B as B by A, then this sign will change. If it is greater, it will become less than sign. Means T1 by T2 should be less than B by A. Okay. If this condition is satisfying, brake will not go in self-locking condition, sorry. And if this equation is not satisfying, brake will go in self-locking. Now here, if you will focus in T1 by T2, can I say T1 by T2 will always be more than 1? Yes sir, it will always be more than 1. Now B by A, here B is greater than A, means B by A will also be greater than 1. Yes sir. So here LHS is also greater than 1 and RHS is also greater than 1. So here both cases possible. Means It might be possible that LHS is less than RHS. If LHS is less than RHS, means this equation is satisfying, means brake will not be in self-locking condition. But it might be possible LHS is more than RHS or equal to RHS. If LHS is more than RHS or equal to RHS, then P will become 0 or negative, means brake will be in self-locking condition. So here both case is possible. In this case, brake can be in self-locking condition also, or it cannot be in self-locking condition. If we want to avoid self-locking condition, if we want to avoid self-locking condition, T1 by T2 must be, T1 by T2 must be greater than B by A, less than. Okay, then don't memorize this relation, try to derive this relation. But if we want the brake should be in self-locking condition, means this condition should not satisfy, means either T1 by T2 equal to B by A or greater than B by A, means here and here both condition is possible. And since both is possible, means this brake can be in self-locking condition or cannot be in self-locking condition. If T1 by T2 is less than this, it will not be in self-locking. If T1 by T2 is greater than equal to this, it will be in self-locking. Okay, and it is self-energized due to tension T1. But in earlier case, it was also self-energizing, but due to tension T2. And if it is self-energized due to tension T2, it will never come in self-locking condition. Means, can I say differential band brake, whether drum is, what you can remember, in differential band brake, whether drum is rotating clockwise or anti-clockwise, it will always be self-energizing brake. Whether it is due to T1 or T1, that T2 or T1, that is different thing, but it will also always self-energizing brake. Now for self-locking, if brake is self-energizing due to tension T2, means slack side tension, then you can conclude it will never come in self-locking condition, like in this case. But if it is self-energizing due to large tension, that is tension T1, then it can be in self-locking condition also, and it cannot be in self-locking condition, means both cases possible. In that case, if examiner is asking what condition we need to satisfy to avoid self-locking, then derive that equation. Don't memorize this. By equating P greater than 0, derive that equation. Whatever condition will come, if that condition is satisfying, brake will not be in self-locking condition. If that condition is not satisfying, brake will be in self-locking condition. But do this derivation when it is self-energizing due to tension T1. If brake is self-energizing due to tension T2, conclude without deriving, it will never go in self-locking condition. You can remember this regarding differential band brake. Means simple band brake is will never be in self-energizing, brake, whether it clockwise or anti-clockwise rotation. If it is never self-energizing, it will never go in self-locking condition. Regarding differential band brake will be self-energizing for both rotation drum, whether it is rotating clockwise or anti-clockwise. Only difference is if differential band brake is self-energizing due to slack side tension, that is T2, in that case it will never go in self-locking condition. But if differential band brake is self-energizing due to large tension, that is T1, then it can be in self-locking and it cannot be in self-locking. So if examiner is asking condition to avoid self-locking, in that case only derive that relation by equating P greater than 0. And this relation is coming for this question. So to avoid self-locking, this condition we need to satisfy, and if it is not satisfying, the brake will be in self-locking condition. Okay, so this is the conclusion regarding differential band brake. So student, here we will discuss one question from differential band brake. What is it is MSQ, means more than one option can be correct. What this question is saying, a differential band brake as shown in figure has an angle of contact of 225 degree, that is theta is given. It is 225 degree. Convert this into radian. In radian it will be 225 divided by 180 into pi radian, and it will come 225 divided by 180 into pi. This is coming in radian, it is coming 3.927 radian. Okay. Diameter of brake drum is 400 mm. Diameter is 400 mm, that is 0.4 meter. So radius will be 0.2 meter. Yes sir. The brake is to sustain the torque of 400 Newton meter, means braking torque is given, that is TB, 400 Newton meter. Braking torque is given, means by using braking torque we can find the one of the relation between T1 and T2, because braking torque is T1 minus T2 into RE, and since TB is given, we can find one relation between T1 and T2. Coefficient of friction between the band and drum is 0.25, that is mu is given. Here mu is given, theta is given, means we can find one more relation between T1 and T2, because T1 by T2 is equal to e to the power mu theta. So by using mu and theta, we can find one relation between T1 and T2. Braking torque is given, means we can find another equation between T1 and T2. Means ultimately we can find value of both T1 and T2. Now what examiner is asking, what will be braking effort for clockwise rotation? Option A and option C. Both is asking what will be the braking effort for clockwise rotation in drum. And D is asking braking effort for anti-clockwise rotation of drum. Here option is hidden due to this toolbar. Here it is mentioned for clockwise rotation braking effort is 966.23. Option C is saying for clockwise rotation braking effort is 132.885 Newton. Option B is this. Option D is saying for anti-clockwise rotation of drum braking effort is 966.23 Newton. These are the four options. But whatever the rotation of drum, whether clockwise or anti-clockwise, since braking torque is fixed, so relation between T1 and T2 will be fixed. That is, since mu and theta is also fixed, another relation between T1 and T2 will also be fixed. Means here, whether it is drum is rotating clockwise or rotating anti-clockwise, the value of T1 and T2 will remain same, because braking torque is also given and mu theta is given, means one more relation between T1 and T2 is given. So first we will find value of T1 T2. How? First T1 by T2 will be equal to e to the power mu theta. Yes sir, e to the power mu theta. Here mu is 0.25 and theta, that is angle of contact in radian, is 3.927. So from this relation we will get one relation between T1 and T2, and this relation will come e to the power 0.25 into 3.927. It is coming T1 is equal to 2.6691 T2. Suppose this equation I am referring as 1. Now in question braking and torque is given. What is the formula to braking torque? It is T1 minus T2 into Re. Braking torque is given 400 Newton meter. I am using SI unit. T1 minus T2. Now Re is R plus T by 2, but thickness of band is not given. So we will take Re nearly equal to R, and R is given, it is 0.2 meter. So Re is equal to 0.2. So from this equation we will get one relation between T1 and T2, and it is coming T1 minus T2 is equal to 400 divided by 0.2. It is coming 2000 Newton. So it is another equation, suppose equation 2. Now by solving these two equations we will get the value of T1 and T2, and by solving these two equations value of T1 and T2 is coming, two equation, two unknown you can solve. One relation is T1 minus T2 is equal to 2000, another is T1 is equal to 2.6691 T2. Here T1 is coming, you can check calculation, it is your part, 3198.25 Newton, and T2 it is coming 1198.25 Newton. It is the value of T1 and T2. Okay. Now what we will do, we will find the relation between braking effort P, T1 and T2 by using the FBD of lever and drum, and from that relation, since we have already calculated value of T1 and T2, we can calculate braking effort. But for that we need to know the rotation of drum. So first we will calculate, because examiner asking braking effort for both clockwise and anti-clockwise. So first we are calculating braking effort for clockwise rotation of drum. So first I am calculating braking effort for clockwise rotation of drum. Drum is rotating clockwise. Now we will draw the FBD of band and drum. To draw the FBD of band and drum, band and lever, we will cut band from both sides, means from this side and this side. If we will cut band from both the side, it will look like this. Now at this point draw a arrow which is tension for this band, means which is trying to elongate this band. The arrow which will try to elongate this band, for that we need to take arrow like this, and equal and opposite tension will come here. Similarly apply a arrow which is trying to elongate this band, for that we need to apply tension like this. Okay, and equal and opposite tension will come here. Now we will find which side of this band is tight side and which side is slack side. For that we will use this FBD. Now how to find tight side or slack side? How to find? For that, suppose I am focusing on this side tension. So this side band is attached with drum at this location. So we will find the direction of velocity of this point. Drum is rotating clockwise. So direction of velocity of this point will be this. Now you can see the arrow of this side tension is opposite to velocity. Means this side is tight side. I am denoting tight side tension as T1. And since this is tight side, this other side will be slack side. That is side of tension T2. Now whatever tension is coming here, equal and opposite tension will come here. whatever tension is coming here, equal and opposite tension will come here. Now in this FBD, what we will do, we will take net moment about fulcrum O equal to 0. If we will do this, the moment will be, suppose I am denoting braking effort as P. So moment of braking effort P about O is P into this distance, which is 600. All distance are in mm here, na? Now direction of moment of this effort P about O is clockwise. Suppose I am taking clockwise moment as plus. If you are taking clockwise as plus, we will take anti-clockwise moment as minus. Now this is tension T1, its distance from fulcrum O is 50, so its moment will be T1 into 50. Now direction of movement due to tension T1 about O is clockwise. I am taking clockwise direction as plus. Now this tension is T2, its perpendicular distance from fulcrum O is 200, so its moment about O will be 200 T2. Now moment due to this tension T2 about O is anti-clockwise. I am taking clockwise as plus, so I will take anti-clockwise as minus. That is equal to 0. From this you will find the relation of effort P. It will come, this plus will come this side, will come minus, this minus will come this side, it will become plus. So this relation will be 200 T2 minus 50 T1 upon 600. Means if examiner is asking whether it is self-energizing or not, it is self-energizing due to tension T1. But that is different thing. Right now we have to find the value of effort P. It will come 200 into tension T2. T2 is 1198.25 minus 50 into T1. T1 is 3198.25 divided by 600. So we'll get the magnitude of braking effort P for clockwise rotation of drum, and after solving it is coming. Now it is just calculation. After solving it is coming 132.89 Newton. So for clockwise rotation of drum, braking effort is nearly 132.89, means nearly 133. Since we have done the calculation up to 0.2223 up to 223 decimal place, so it might be possible there might be some difference in actual answer, because due to this approximation. Right now for clockwise rotation of drum, braking effort is 132.89, nearly 133 Newton. So 132.89 for clockwise rotation of drum. Which option is correct? For clockwise it is anti-clockwise, it is clockwise. This option C is correct. For clockwise 132.89 Newton. Means option A is also asking about clockwise, which is incorrect because it is correct. So out of A and C, C is correct. But since it is MSQ, we need to also focus on B and D. And B is D is asking braking effort for anti-clockwise rotation of drum. So now we will calculate braking effort for anti-clockwise rotation of drum. So for that now we will draw this FBD, but for anti-clockwise rotation of drum. Again, at this point apply a arrow which is trying to elongate this band. It will be like this. Equal and opposite tension will come here. Again at this point apply arrow which is trying to elongate this band. Equal and opposite tension will come here. Now we will find which side of this band is tight side or which side is slack side. For this we will use this FBD. Now in this FBD, suppose I am fixing for this side tension, whether it is tight side or slack side I am finding. For that this side band is attached with drum at this location, so we will find the direction of velocity of this point. Drum is rotating anti-clockwise, and for anti-clockwise rotation, direction of velocity of this point will be this. Now you can easily see this direction of this side tension and velocity is same, means this side will be slack side, and I am denoting slack side tension as T2. Since this side is slack side, another side means this side will be tight side, that is the side of tension T1. Now whatever tension is coming here, equal and opposite tension will come here. Sorry, it is T2. Whatever tension is coming here, equal and opposite tension will come here. Now in this FBD, we will take net moment about fulcrum O equal to 0. It will come. I am denoting braking effort as P. So it is P. Its distance from perpendicular distance from O is 600. So its moment will be 600 P. Direction of movement will be clockwise. Suppose I am taking clockwise as plus and anti-clockwise as minus. Now T2, its moment will be, its perpendicular distance from fulcrum is 50. So moment of T2 will be 50 T2. Its direction about O is clockwise. Suppose I am taking clockwise as plus, anti-clockwise minus. Since it is clockwise, I am taking is as positive. Now T1, its perpendicular distance from O is 200. So its moment will be 200 T1. The direction of movement about O will be anti-clockwise. I am taking clockwise plus, means anti-clockwise minus. So it will be minus. That is equal to 0. from this the relation of P will be, this plus will come this side, it become minus, this minus will come this side, it will become plus. So it will be 200 T1 minus 50 T2 from 600. Means this brake is self-energizing due to tension T2. Okay. Now effort P, 200 into what is the value of T1? I think the value of T1 is 3198.25. You can check. Minus 50 into T2. What is the value of T2? T2 is 1198.25 divided by 600. So from this equation we can calculate the value of effort P, and it is coming 200 into 3198.25 minus 50 into 1198.25 divided by 600. After solving, it is coming nearly 966.23 Newton. Means for anti-clockwise rotation of drum, braking effort is 966.23 Newton. Which option correct? In B and D, examiner is asking about anti-clockwise rotation. For anti-clockwise, 138, this option is correct. For anti-clockwise, braking effort is 966.23, means option D is correct. Means out of B and D, the correct option is D. Means for this question, correct answer is option C and option D. Okay. Now, we have completed analysis of differential band brake. Now you have to remember some important relation regarding band brake. Suppose here in this diagram, drum is rotating clockwise. If it is rotating clockwise, this side will be tight side, that is side of tension T1. This side will be slack side, this is side of tension T2. Now, sometime examiner may ask what will be the maximum pressure in drum. So remember the maximum relation of maximum pressure in drum is T1. T1 is tight side tension, divided by R. R is radius of drum, into B. B is width of the band. Okay, you can write R is radius of drum, B is width of the band. I am not going in derivation. You have to remember the maximum pressure in drum will be T1 tight side tension upon RB. Similarly, examiner may ask, since this band is tension, due to this tension in band, stress induced will be tensile stress. Now what will be the expression of tensile stress? Suppose this is the cross section of band. Width of the band I am denoting as B, thickness of the band I am denoting as T. Tension is suppose T. So tensile stress will be T upon area, that is BT. But if we want to calculate maximum tensile stress, we will take maximum tension, and maximum tension is T1. So can I say maximum tensile stress in band? It is coming in band. Maximum tensile stress in band will be T1 divided by BT. So these two relations are important. You can remember this. First relation, maximum pressure will be T1 upon RB. Maximum tension will be T1 upon cross section area of the band, that is width into thickness. Sometime examiner might give the value of permissible tensile stress. So we need to use this relation. Examiner might give permissible pressure. It is coming on drum. Okay. So permissible pressure. So from this relation you can use. So these two relations are important. So we have completed the analysis of differential band brake also. Means we have completed this unit. Okay. One question we will discuss from this topic also, means maximum pressure and maximum tensile stress. Then this topic will get end. This is one question. What this question is saying, for the differential band brake shown in figure, width of the band is given, that is B, 100 mm. Thickness of the band is given, that is 3 mm. Permissible tensile stress, suppose I am denoting permissible tensile stress is sigma TP. It is given 40 megapascal, means Newton per mm square. Means can I say actual maximum tensile stress? Actual maximum tensile stress either should be equal to 40 or less than 40. And to find limiting value, we will equate this with 40. Coefficient of friction is given, that is mu 0.3 between band and drum. Radius of drum, that is R, is given 300. It is mm. By typing, it is typing error. Means in meter it will be 0.3 meter. Now we have to find braking torque capacity of the brake. Now to find braking torque, what is the relation of braking torque? It is T1 minus T2 into RE. Now RE, R and T is given, means you can calculate RE. RE is R plus T by 2. But for that we need to find T1 and T2. Since maximum tensile stress is given, can I find T1? Because formula of maximum tensile stress is T1 upon BT, and width and thickness is given. So we can find T1. Now in this question, mu and theta is given because it is mu, and from this diagram you can see angle of contact theta. Angle of contact theta is 240 degree. Angle of contact theta is 240 degree, and you can convert this into radian. If we will convert this into radian, it will be 240 divided by 180 into pi. In radian, it is coming 4.1888 radian. So in question, since mu theta is given, we will find the one relation between T1, T2. It will be T1 by T2 equal to e to the power mu theta. From maximum tensile relation, we can find T1. Then by using the relation of T1 and T2, we can find T2. By calculating both T1 and T2, by using this relation, we can find breaking torque. Okay, so we can easily find breaking torque here. How? First, maximum tensile stress should be less than equal to 40. Now to find limiting value, we will equate maximum tensile stress with 40. Now maximum tensile stress is nothing but T1 upon width into thickness. It is equal to 40. So T1 will be 40 into width into thickness. And since this 40 is in Newton per mm square, we'll put this area in mm square. Means we'll take width and thickness in mm here, because this is in Newton per mm square. So width in mm is 100 mm and thickness in mm is 3. So from this we will get the value of T1 in Newton, because sigma T is in Newton per mm square, area is in mm square, so T will come in Newton, and it is coming 40 into 100 into 3, 12,000 Newton. So it is the value of T1. Now by using the relation between T1 and T2, what is the relation? T1 by T2 is equal to e to the power mu theta. Mu is 0.3 and theta in radian is 4.1888. From this relation we can find T2, because T1 we have already calculated, it is 1200 Newton. So from this equation we will get the value of T2. After solving, it will come e to the power T2 is coming 3415.3045 Newton. And since we have calculated T1 and T2, you can calculate braking torque. The braking torque will be T1 minus T2 into Re. Here I will use SI unit. So braking torque will come in Newton meter. T1 is 12,000 minus T2. T2 is 3415 3415.3045 into Re. Re is R plus T by 2. R is 0.3 meter plus T. Thickness is mm is 3 mm. So in meter it will be 0.003 meter. So T by 2 means 0.003 divided by 2. From this equation we can calculate braking torque, and how much it is coming. It is coming 2588.285 Newton meter. So braking torque is coming 2588.285 Newton meter. Okay. Second, examiner asking actuating force. Actuating force means braking effort. Suppose I am denoting braking effort means examiner asking about P. So to find P, T1, T2 we have already calculated. So by using FBD of this system, we can find relation between P and T1 and T2. From this relation we can find P. So to draw this FBD, drum is rotating clockwise. We need to cut both sides of bend like this and like this. And if we will draw FBD, first we will find the tension. The tension of this side will be like this. Tension of this side will be like this. Equal and opposite tension will come here. Now we will find which side of this band is tight side or slack side. For that we will use this FBD. Now suppose in this FBD I am focusing in this side. So this side band is attached with drum at this location. So we will find the velocity of this point. Since drum is rotating clockwise, velocity of this point will be this. Now this side tension or this velocity direction is same. Means this side of the band will be slack side, because direction of tension and velocity is same. Means it is the side of tension T2. It is the side of tension T2. So it will be tight side, and tight side tension I am denoting as T1. Equal and opposite tension will come here. Equal and opposite tension will come here. After that, in the FBD of lever, we'll take net moment about fulcrum of equal to 0. If we'll take this moment, it will be effort P, its moment about O. See carefully, this distance is 750, this distance is 200. So this distance will be 950 mm. So moment of effort P about O is 950 into P, and direction is clockwise. Suppose I am taking clockwise as positive, then I will take anti-clockwise as negative. Now T2, its movement about O will be its perpendicular distance from O is 200, so its movement will be 200 T2. Now direction of movement about O is anti-clockwise. I am taking anti-clockwise as minus. Now T1, its distance from O is 50, so its movement will be 50 T1. Direction of movement about O is clockwise. I am taking clockwise as plus. That is equal to 0. So P will be, after solving, 200 T2 minus 50 T1 upon 950. P will be 200 T2. Value of T2 we have already calculated. It is 3415.3045. You can check. Minus 50 T1 is 12,000 divided by 950. From this equation we can calculate the value of braking effort P. And how much it is coming? It is coming 200 into 3415.3045 minus 50 into 12,000 divided by 950. It is coming 87.432 Newton. Check calculation. It is your part. Yes, it is coming 87.432 Newton. So braking effort required is, for this question, is 87.432 Newton. Okay, so it is the solution of this question. So we have completed the types of brake, analysis of shoe brake, analysis of bend brake. Means we have completed the entire topic of bend, so entire topic of brake of machine subject with respect to gate examination. Okay, so this lecture is completed. It is our team Drona of mechanical team in gate Wallah. These are all the faculty. He is Devendra sir, who is deal thermodynamics with you. He is Swadesh sir, he will deal production with you. Vinod sir, applied thermodynamics. Aditya sir, production and industrial. Ratan sir, aptitude. It is me. It is Vishal sir, he will deal mathematics with you. He is Vinay sir, he will also deal mathematics with you, FM with you. This is Kuldeep sir. So it is entire team Drona. Okay. Now, thank you. And we, in this one short series, in another day we will meet with another topic. Okay.